National Conference on Automated Knowledge-Based Construction. I hope you and your families are all well in this unusual and difficult season. I hope that you're finding strength in the difficulties and opportunities to help others. I'm Andrew McCallum, Co-General Chair with Samir Singh, from whom all of you will also hear soon. So why last year did we decide to create a new conference? First, many of the conferences that we know and love have, due to exploding interest in AI and data science, become so large that they suffer under their own weight, lacking both the close-knit culture that longtime attendees cherish and also a manageable social atmosphere with breathing space that helps newcomers feel welcome. Broadly, CS is growing dramatically, and it's only sensible for growth to result in new communities and conferences to foster them. And second, the time is ripe for new scientific advances and impacts in knowledge bases. Research in knowledge bases is many-faceted, with contributions coming from many traditionally separate subfields. Yet there wasn't previously a venue that brought us all together. AKBC strives to provide that venue. So next slide. So after nearly 10 years of highly attended AKBC workshops, last year we created a new conference with its first instantiation in Amherst, Massachusetts. Next slide. We were due to be in beautiful Irvine, California this year, but that will now wait for a future instantiation of the conference. And like so many conferences, we are virtual this year. Samir and the program chairs have done tremendous and creative work to make your virtual attendance as interactive, engaging, and scientifically productive as possible. And we encourage you to actively participate, to ask questions, to join chats, to find old friends, and also make new friends. We have a dedicated, energetic, and caring set of organizers this year to which we all owe our gratitude. They include Samir Singh, my co-general chair, who also led fundraising this year and the creation of the online virtual conference tools. Also, Zachary Ives and Amanda Stent, our workshop chairs, Matt Gardner, local chair, who also contributed greatly to the virtual conference. And of course, our intrepid, insightful, brilliant program chairs, Hanana Hajishiri-Itzi and Dipanjan Das, who will now take the stage.
Thank you very much, Andrew, for the general introduction. Hi, everyone. I'm Dipanjan Das. I will represent the program chairs, Hana Haji Shirzi and myself, and I'll give you a set of statistics regarding this year's AKBC conference. So we had an abstract submission deadline first, and then a paper submission, and we received 91 abstracts. After deduplication and some abstracts not following through to the submission, we had 67 papers that were submitted. After some desk rejects and some withdrawals, 58 papers went through the full review process, out of which 29 papers were accepted. This year's conference has a diverse set of areas. They come from NLP and information extraction, question answering and reasoning, applications, human computation and crowdsourcing, databases, relational AI, knowledge cleansing and integration. We had 16 extraordinary area chairs from a diverse set of backgrounds and research areas coming from all over the world, who helped us review and select papers. Briefly, the conference, the highlights are basically we have invited speakers on every day, and then paper presentations that would be live streamed from pre-recorded videos, and also live interactions via poster sessions, both with the authors as well as the invited speakers. So on day one, today we have 4 invited talks from William Cohen, Jure Leskovec, Jamie Taylor, and Chin Luna Dong. On day 2, we have 5 invited talks presented by Luke Zettelmoyer, Nadapa Nakashole, Emma Strubel, Andrew Su, and Dee Yang. On the 3rd day, we have 3 4 presentations. We have 4 workshops on the 4th day, on June 25th, on 4 areas. natural language processing and data mining for scientific text, bias in automated knowledge-based construction, structured and unstructured KBs, and knowledge bases and multiple modalities. We had a best paper committee formed by participants and invited speakers and area chairs, a selection of them outside of the organizing committee, Hung Ji, Ivan Titov, and Di Yang, who helped us select 5 spotlight papers. And the same committee also decided a best paper who we will announce at the end of the conference on the closing session. And we will also have a People's Choice Award. We will send out a link where attendees could vote on the best presentation, and that will also be announced on the final day. And now I will hand over to Samir Singh, who led the development of the virtual conference setup for AKBC.
All right, welcome everyone. So I'm going to talk a little bit about how the conference is going to take place. Essentially, we have 3 modes of interactions for you to interact with everyone else. The first one is going to be the live video sessions, where presumably you already are by clicking on the live link on the website. The second mode of interaction is going to be Zoom meetings, and you should see these Zoom sort of pop-ups all over the website, where if you directly click on the link, you should be able to join without any need for login or anything. If there's any problem, do reach out to us. And the last mode of interaction is chat rooms, which is available on the website, or you can go to akbc.rocket.chat directly and log in there. Same credentials as the website. There are lots of rooms there. Each paper has a room. There are general chat rooms where you should introduce yourself. We'll also be doing announcements from us, from the workshop organizers, things like that. And then if you have any issues or questions, you should reach out to us using the channel #helpdesk. So essentially, the virtual conference is going to have 3 kinds of sessions. The first session is going to be live session, which is this one. It's going to include the opening session and the closing session, along with the invited talks, which is the bread and butter of this conference. I also want to say that we are also going to be streaming the paper talks, although these talks are available on the website. In case you haven't in case you haven't seen them, you can see them in the live session. And in the end, we'll also have the best paper award. So all of this is going to be live through this stream. Our second mode of set of sessions are going to be the poster sessions. These are going to be Zoom meetings where you're going to be interacting with the authors of the papers. To some degree, we'll assume you've seen the talks, but if you haven't, you can always talk to the authors about it. If you have any questions, any issues, this is the time to chat with them. Each meeting is going to have maybe 2 papers per meeting on days 2 and 3. Our last kind of session is going to be the hallway chats at the end of each day. This is also primarily relying on Zoom meetings, where you will be able to speak with invited speakers, meet with them in Zoom meetings in groups. We also have rooms set up for meeting other people randomly. So if you just want to not talk to the invited speakers and just hang out with other attendees, you can go there. And finally, we're going to have virtual booths set up for all of our sponsors. And you can go to them, ask them about their company, ask them about their job opportunities, and in this economic environment, it might be good to get a head start on that. And so what I want to point out here is something like invited talks actually spreads multiple sessions. You're going to be watching them live. Their pre-recorded videos are not available. And then you're going to be chatting with them during hallway chats. Focusing a little bit more on the papers, you'll notice that on the website, each paper has a web page, which has the pre-recorded videos and slides. And so if you're specifically interested in a few papers, you should do that already. We have links to the whole PDF, the reviews, the discussion, non-open review, and all of that on there as well. We also have embedded chat for that, specifically for that paper, where you can ask them questions or talk to other people who have questions about the paper. And then we'll have direct links to Zoom as well. So again, there are going to be 3 modes of interactions even for a paper. in the chat room. You can ask questions, have other discussions with them. You'll see the live video stream of the pre-recorded talks during the lightning talk sessions. And finally, we have links to the Zoom meeting. So in the end, I want to, yeah, we can, next slide, yeah. In the end, I really want to thank our sponsors, SAP, Microsoft, Relational AI, IBM, Google, PIMCO, and Oracle Labs. These guys really came through. I think we were, not only are they supporting this new conference, but the transition from a physical event to a virtual event is tricky, especially when it comes to the logistics. And all these companies have been pretty supportive of what we threw at them. So I really encourage everyone to go to their virtual booths for the companies that are planning to have those at the end of every day. Okay, so that's all we have in terms of the opening remarks. We're a little bit early, it seems like it. So maybe we should start with the invited talk a little early or wait for a few minutes. Let's wait for a few minutes. Maybe we'll.
Yeah, maybe let's start at 11:18 and then we can hand it over.
Okay, so, okay, we'll maybe start in 5 minutes then. Okay.
I suppose people could use this time to make sure that they can log into the chats, maybe find some papers that they, especially whose chat sessions they want to attend.
Okay. I'll just share a generic set of slides here.
So I think we should get started. William, please start presenting your slides. Um, our first invited talk of the conference is by William Cohen. William, it's my pleasure to introduce him. He is a principal scientist at Google and is based in Google's Pittsburgh office. Before being at Google, William was a professor at the machine learning department at Carnegie Mellon University. He has had an illustrious career in machine learning. He was the president of the International Machine Learning Society. He served as an editor of various publications, including Morgan and Claypool, a series of machine learning books, the journal Machine Learning, the journal Artificial Intelligence, JMLR, Journal of Artificial Intelligence Research, and so forth. He has been a general chair and the program co-chair of the ICML conference several times. He was the co-chair of one of the first editions of the AAAI conference on weblogs and social media. He's the winner of Test of Time awards at both SIGMOD and SIG-IR. He's a AAAI fellow. It's our pleasure to have him speak at AKBC. William, please take it away.
Thank you so much, Dipanjan, for the introduction. I hope everybody can hear me. There's like not a whole lot of feedback with these Zoom presentations, but we'll try and do our best. I'd like to thank the organizers for inviting me here. It's great to be with all of you. Let's go ahead and get started with the work that I've been doing, and I should say with many colleagues, primarily at Google, a few at CMU. Here's sort of the outline. What I'm going to be talking about today is basically neural versions of an old AI chestnut, which is languages that are designed for querying a knowledge base. So this is something that people have been looking at AI from the very beginning. We'll be talking about doing this in a neural way. In particular, I'm going to talk about a couple of different query languages. One called NQL for neural query language, and a more recent one. Once I've talked about those, I'll talk a little bit kind of going forward. This is some very recent work on taking these query languages and embedding them inside a large neural language model. So that's basically the plan for the talk. And I'm going to start out by just talking about why I'm working on this problem. Why do you want to neuralize a knowledge-based query language? What's the motivation for that? Let's look first at a problem that probably most of you guys are familiar with, knowledge-based completion, okay? So knowledge-based completion, you've got some true triples, which are, suggested by this knowledge base in the upper right-hand corner. And based on those true triples, you want to sort of extrapolate from those and discover other triples that are plausibly true given the ones that you know about. So here, I work at Google. My co-author, Haishan Sun, is somebody I collaborate with. It's possible that he also works at Google. So you'd like to generalize from the things you know to other plausible things. And the kind of standard way of doing this in knowledge-based completion is with a neural function, which basically takes a triple and asks and scores it as to whether it's likely to be true or not. And usually this is based on some function based on embeddings that represent each entity in relation. So one very common technique, for example, is there's an embedding for the head and the relation, and you add them up, and that should approximate the embedding for the tail. It's the trans-Z method. But in general, if you have any thing that looks something like this, if you combine the head and tail, and you come up with that head and relation, and you come up with some approximation of the tail, and you have some way of retrieving approximate vectors, say some sort of like top K similarity retrieval method, then you can also do this, use a knowledge base embedding to do retrieval of and sort of answering certain types of simple queries. So knowledge base completion is not entirely related to the problem of querying a knowledge base, but it's also not entirely the same. So when you talk about querying a knowledge base in a traditional neural context, you're trying to do something a little bit different. Again, you're starting with true triples, facts that we know about, and you're trying to go from those facts to other additional facts. Okay, but the additional facts you're trying to find are ones that are entailed by logical rules. So to make a plausible, example based on this case, supposing someone gives you a rule that says, well, if you work at, if Y works at company Z and X reports to Y, then X also works at company Z. Okay, so if you have that rule, then you could extrapolate, if we have the right facts, we can extrapolate a new fact, again, suggesting that Hai-Chun-san works at Google. Okay, and if you think about it, there's actually something even a little bit simpler here. Besides firing a rule and sort of running logical inference until you get some sort of deductive closure, an even simpler thing is just figuring out how to evaluate the antecedent of that rule. The kind of primitive thing you can think about here is answering a compositional structured query, like this conjunction right here. And these often involve retrieving things, okay? So a structured query is a little bit like a body of a rule. This is what we're going to be talking about here. This is a sort of like the kind of first rung on the ladder of increasingly more powerful types of logical inference. And I'm going to talk about a very simple type of query language, which is basically a data flow language. So something a little bit like, Spark or Plume or Pig, if you're familiar with any of these things. So we'd have operations that take for a set of objects, which just contains the set Google, and then you follow the inverse of the worksat relation. So these are all the Google employees, and then you follow another link to find all the people that report to those. So that's a very simple query language. It lets you answer a certain class of structured queries. And what I'm going to be talking about here is neural query languages of this sort. Okay, and I'm going to focus on ones that can reliably get the same answers as logical knowledge representation systems, but use differentiable methods. So we're really looking at solving the problem suggested by this blue rectangle over here. So we're looking at logical inference, not generalization in a KBC sort of case. Now, combining these two things and looking at things, what you do structured queries and generalize is actually a very interesting task. I'll say a few words about it in this talk. From the abstract, I believe that the very next invited talk from Yuri is going to talk about this in more detail. I'm very excited to hear about that. But here, again, I'm focusing on basically logical entailment, not generalization. So why do you want to do this? Here's a simple kind of motivating problem. And that is the problem of knowledge-based question answering. So a knowledge-based question answering, you start with a natural language question, like the one here. And what you usually do is you apply some neural method, which gives you a semantic parse of that question, which gives you some sort of symbolically interpretable logical form that you can then run against your knowledge base, okay? So we've got one neural part of this problem, and then we have this one symbolic part of this problem. So what we'd like to do is actually neuralize the whole process. So if we have a neural knowledge-based query language, then we don't need to have this symbolic step. And one advantage of that is we don't need to get training data, which maps us from the natural language query to the symbolic form. Instead, we can think about a process which goes straight from the query through the logical form to the predicted answers. And we compare those with the target answers. So we can do training in a more kind of end-to-end process. So in this sort of setting, the actual query is going to be latent. It's going to just be something that the neural network is going to have to figure out. And hopefully it's going to be constrained by the answers you want to get and other biases you might put in. And the reason we want to look at things that behave as logical systems is if these predicted answers are actually the ones that are entailed by the knowledge base in a logical setting, which is true at least for many of the data sets people are looking at now for this task, then if you actually generalize the knowledge base in the process of producing these answers, what you're really doing is you're just sort of jittering what the predicted answers look like, right? And you're introducing something which looks like noise. So you're adding some plausible generalizations, but they're going to be different from the target answers that you're trying to get, even if you have the correct underlying logical form. So in this particular case, generalization is not what you want to do. You want to get the same answers as the logical knowledge representation system. Okay, So that's the motivation. Now let's look at sort of a first example of what one of these neural query languages might look like. So this is some work that was published in the most recent iClear 2020. So this was done last year. And I'll start out with just some very concrete examples. So this is a very kind of low-level description, but you set up an object called a context, and then that object has got a bunch of functions that hang off it that let you declare the schema of the knowledge base, load in data, and declare types and things like that. Then you can construct sets. So the simplest thing is just to construct a singleton set that just has one element. So this string here is basically an ID for this particular entity. It has type person, and we're just going to create a singleton set here called Henry VIII, which corresponds to the King of England, Henry VIII, who famously had 6 wives. And if I apply this .wife function, where wife is a relation, then I'm basically sort of going to follow that relation through and find the set of all entities that are wives of Henry VIII. So all these expressions evaluate to sets, and in fact, they evaluate to weighted sets. So there's a number associated with every set. So here would just be 1.0. And we can compose these things. So we've got set operations like this is a union and intersection. So we can say, let's take the sons or daughters of Henry VIII. So that's all his children. And then we can take the sons of that set. So that would be the grandsons of Henry VIII. And there's also a little bit of second order logical reasoning, okay? So you can also have a variable, which is a relation, and then we have the special construct here, follow. So we can follow a variable relation. And in fact, that relation R1 and R2 is a set of relations. So it's just another set. Relations are essentially entities of a special type in this framework, okay? So if I wanted to get grandsons, I would let R1 be son, union, daughter, or that doubleton set, okay? And I would let R2 be son. And then I get exactly the same semantics as this example right here. And one thing that's interesting about this is that's also something that can be produced in some other way, right? So rather than being a hard set, it could be a weighted set. You could have, some very approximate weights, maybe even ones that are produced by a neural function. The semantics of this are all defined. So that gives us a possibility of learning these parameters of the query. So the semantics for NQL are very simple. Every set is basically just stored as a k-hot vector. So if you've got 1,000,000 entities, that vector is 1,000,000 components long. And the weight for each entity component is its weight in that set. So these context.1 just gives you a one-hot vector. Follow is multiplying this vector by the adjacency matrix for the relation. So this is a very large, very sparse matrix. Okay, so we have to use sparse matrix technology to make this work. Follow a relation R basically is a mixture of these things. So you're just like sort of looking at a weighted mixture of these matrix multiplications. And k-hot vectors have nice properties if you want to do unions and intersections. So the implementation doesn't quite follow this statement of the semantics. It's actually implemented with just 3 large sparse matrices. It's relatively compact. You can actually scale this to tens of millions of triples on a handful of GPUs. It does distribute. It scales very well with the number of relations, so it's fine if you have thousands or tens of thousands of relations. So you can do not inconsiderable knowledge-based processing in this framework. And let's, again, kind of drill in a little bit. So this is what the NQL syntax roughly would be for this. Actually, this, -1 is not expressed exactly the same way, but this is roughly the NQL syntax. So in order to implement a system that would do this kind of query answering, what we would do is we get some training data for the target answers, okay? And we define some sort of template that describes what the structured query is going to look like, all right? So the template's going to be given, and we're going to fill in the slots of the template, and those will all be neural functions. So we have some neural function which takes, some representation of the textual question, extracts. In this case, we have basically an intersection of two follow operations. So we're going to basically derive the parameters for those, okay, evaluate them, get a predictive answers, and train through. And when we're training here, the semantics of the query language are basically the fact that it's differentiable is what lets us take these target answers, take that loss, and push it through the neural query language, right? And train this part right here, which is really the interesting part. This is the natural language understanding part. Okay. So if we have a slightly more complicated setting, so maybe we don't know exactly what the format of our questions are going to be, we might have to construct multiple templates. That's okay. In the simplest case, you can just take a new template and sort of add a union of that with the old template. In a more complicated case, you might want to have some sort of neural function that sort of switches between those appropriately. You can even do something a little bit more complicated. So in the iClear paper, there's a discussion of how to use an encoder-decoder approach that would let you produce some very large number of NQL expressions rather than sort of like just a simple template. So how does this work? So here's some numbers. So one of the most widely used data sets for knowledge-based question answering is something called Web Questions SP for semantic parsing. It's over an old branch of Freebase. We're actually running over a subset of that, which has enough triples to answer all these questions. So it's about 40 million triples, about 13 million entities. There are only 700 relations, but it's a decent sized knowledge base. There's a relatively small number of questions. Every question in the data set we have is associated with a set of entities that appear in that question. So in our template, we don't have to worry about filling that in. We basically just need to fill in the relations. And all the questions are 1 or 2 hop questions through the knowledge base. So we essentially learned 3 relations, one that we're using for 1 hop questions and 2 we're using for these 2 hop questions. And this is the whole model that we need to use expressed in this NQL syntax. Well, almost the whole model. The loss is softmax cross entropy of this output. And we, of course, have to define what these functions are. In the experiments I'm going to talk about, this is the simplest thing you can imagine. So this is basically, a mean pooled bag of word encoding and then a linear projection on top of that. So the functions that produce these relations are extremely simple. Okay. So here's how this works for WebQSP, and I'm comparing it here to a key value memory baseline. It works fairly well. One thing that's pretty nice, here's another set of questions. These are all 1 and 2 hop questions. So on average, they're not very many hops. This is another KBQA data set where there are 1 hop, 2 hop, and 3 hop questions. So these are nothing but 2 hop questions. And we can see performance drops off fairly slowly as the complexity of the inferences gets larger. Here's yet another task. Knowledge-based question answering is very similar to a certain approach to knowledge-based completion. So in knowledge-based question answering, there's a query which depends directly on the question. In KBC, in completion, you typically have a head entity and a relation name, and the query depends on that. So you'll have many examples that go with the same head relation pair. So we'll have many examples. So the structure of the conditional control of this latent query is a little bit different, but essentially it's the same idea. You construct this latent query based on other relations, and then you predict answers and get the loss. So here are again some numbers. This is NQL compared to a number of recent or fairly competitive knowledge-based completion methods for the NEL 995 data. This is another synthetic task where we've sort of looked at things which have extremely long, deep inference chains. So this is like sort of 10 hop inference chains. We can see both of these things are pretty competitive. It's pretty competitive on both of these tasks. And then this is like sort of going back to the knowledge-based QA tasks. So we've added a couple of things. One is some synthetic multi-hop questions up to 5 hops here, up to 10 hops here. And this is a KBQA sort of setting. This is now comparing with the state of the art. Actually, I lie. This is the state of the art at submission time of the paper. So things have moved a little bit past then. But these are sort of very strong baselines for these problems. So again, we're seeing NQL is, even with this very simple model, fairly competitive. But it's not always the best. And there are some cases where it actually underperforms state-of-the-art models by a substantial amount. Okay, so what can we do about that? So why is this happening? So this is giving us the same answers as logical KR systems, but it's doing it in what's arguably the wrong way. It's a very localist representation. These sparse matrices are telling you exactly what's in the knowledge base, but they're very hard to generalize. And in particular, when you're learning a relation variable here, okay, that's a hard task. What you're doing here is you're predicting a k-hot vector over 700 different possible relations. So you're basically predicting a subset of relation IDs for relations that sort of have arbitrary integer codes. That's not an easy problem. And posing the problem that way ignores really a lot of the most interesting work in neural representation learning that's happened over the last 15, 20 years. So the next thing we want to talk about is basically getting fidelity, faithfulness to logical reasoning in a language that is able to naturally exploit neural representations based on embeddings. Okay, so I should say there's a somewhat obvious solution to this. Particularly if Yuri had given his talk first, you would all say, well, why don't you use something like query to box, right? Or in general, why don't you use some sort of knowledge-based embedding strategy? Those are all differentiable, right? And can we just simply extend it to handle these sorts of logical queries? So the problem is these things have been designed for and tested on this task of generalization, not on this task of faithful logical reasoning. And it turns out, if you look at how they do on faithful logical reasoning, they don't tend to do that well. They generalize from the knowledge base, but they from the existing facts, but they don't do very well at modeling true entailment. So we're going to have to add a few new things. So the two new things that are added here, and I should say this is also work that's very recent. It's in submission. There's an archive paper I can point to if you're interested. But the two new things here is there's a new representation for a set of entities. And there's a new process for doing essentially the relation following step, which is sometimes called projection in this literature, which is based on neural retrieval rather than a geometric operation in embedding space. So I'm going to take a couple of minutes and talk through those in a little bit of detail. And this is work primarily with Hai-Chin Sun. Well, I say with, it's like he's doing the work and I'm here talking about it. So this language, MQL for embedding query language, supports the same operations as NQL. So externally it looks the same, but the representation is really different. So everything is represented, every set is represented by this pair, including a centroid and a sketch. So what does this look like? So we're going to describe two things. One is a geometric region where the entities, where the embeddings for the entities live. And I'm going to describe that by just specifying the centroid, which sort of defines maybe a sphere around that. Okay. But a sphere, of course, is not a very good representation of a complex geometric shape, right? It's not a good representation of a set if you're trying to capture the fine-grained information in the knowledge base. So we're going to need to add a little bit of additional information to help us memorize details. So what we're doing here is adding here is something called a Countman sketch. You can kind of think about this as a continuous Bloom filter, if you're familiar with Bloom filters. So you basically sort of use multiple hashes to associate an ID of an entity with a number. So you can think of this as approximating a k-hot vector with high probability. So if the set is small, you can do this relatively well. And relatively well means most of the time you'll get the right answer, and every once in a while, maybe one time in 100 you'll get the wrong answer when you do that query. It's a matrix that will typically be sparse, so it'll have a lot of zeros, but not an enormous number of zeros. It's perfectly reasonable to represent this with ordinary dense matrix representations. So you don't have to worry about sparse matrix math being implemented in your GPU or your tensor processing unit or something. And these sketches are not large in our experiments. So from this representation, what can you do? So the simplest thing that you want to be able to do is actually find the entities that are in that set. So here's how you do it. What you do is you first find the centroid and you do a top K search on your table of embeddings to find all the things that are close to that centroid. So since we don't really believe that geometric space is going to be perfect, we have to be a little bit promiscuous here. So we're going to pick more things than we think are going to be in the final set. One way of thinking about AK is it's basically a fine-grained type for the elements in the set. You're taking all the things of that type. Those are the candidates. Then we're going to rescore them using the count and sketch. All right. So we don't sketch. So critically, we don't query the sketch millions of times. We don't query it for every entity. So even though there's some probability of getting a wrong answer, we still don't really need a very large sketch. If I want to predict a set, so let's say I've got a neural function that's going to predict a set of relations, the problem now looks really different. So I have to predict the centroid and the sketch. The sketch will just be vacuous, right? I'm going to sort of put all the work that the predictor does on predicting the embedding. So now what I'm doing is I'm basically predicting a point in embedding space, which is a much more structured problem for prediction. That's another kind of key point. So Countman sketches have these very nice closure properties. If you've got two sketches, one for set X and one for set Y, then you can do very simple operations on the sketch, simple linear operations that will give you the union and intersection. So if I want to do a union of two sets, there's actually a very easy way of doing that. What I do is I simply union the sketches using these simple operations, and then I'll average the centroids. So that works great if the fine-grained types are very similar. And for the experiments I'll be talking about, usually that's all you care about. So the last operation is this follow operation. So I want to find a set of objects X, and I want to basically follow a weighted set of relations R. So the usual approach in knowledge base embedding methods is you do some sort of linear transformation of that subspace. So if my set X is X3 and X4, I will do some transformation, and everything else is going to follow the same transformation. Everything else associated with that relation is going to follow that same transformation, which may or may not give me the particular things I want to have, right? So if the actual Ys that I'd like to have, the things that are actually related to X4 is Y4 and actually related to X3 is Y3, this may not give me quite the right result because, of course, I've got a low dimensional approximation here. So what we're going to do is something a little bit different. Instead, essentially, the idea is I'm going to look up some triples. So I've got embeddings of X1 and Y1. These are the actual embeddings associated with a knowledge-based triple. Okay, so I'll look up the right embeddings that go along with X4 and X3, which would be Y4 and Y3. And then, of course, I've got to push this back into a centroid sketch representation. So at some point, there's going to be a little bit of loss of information again. So we'll see how that works. So this is essentially the idea. What we actually do is we build a triple table where we've got 3 parts: relation, head, and tail. We have a centroid for the relation and the head, and those are used as a query, and then we filter using the sketches. So this is very fast. It just uses one top K retrieval. Couple of details here. This is now we're training a set of embeddings, so we have to do that. We do this by generating a bunch of synthetic queries. But there are lots of things that we can do. In particular, if we want to bias the embeddings towards something useful, maybe using some sort of pre-trained embeddings, we can do that. And when we're done, we do the same thing we did with MQL. We basically fix this logical inference scheme, and we train the rest of the model through that. All right. So here's some examples. So these are synthetic problems, and this is from Yuri's recent paper. So the state of the art for this task, generalizing using a query language, is the system query to box that I hope he's going to talk about soon. So we're looking at that in a very different context. He's looking at generalization. We're looking at, faithfully looking at the logical semantics. And the important point is there's a huge difference here. So these are sort of in the 90s, and these numbers are often in the 50s or lower. And both things contribute. So MQL minus is using the retrieval, but not the sketch. Okay, and we can see that does improve performance a lot, but it doesn't get you sort of all the way there. And then finally, I'm going to look at this in the knowledge base QA task. Here's these two kind of standard problems. The 3-hop movie questions, meta QA. This is the web questions SP. Okay. We're getting better than the state of the art in one case, much closer to the state of art in the other. I got it. Finally, here's a little bit of an ablation study. So we actually didn't cover all the cases in that 2-line model. There's one more rare case. If we actually add that to the NQL model, then we do get improvements over the state of the art. And then this is again an ablation study where we disable the sketches.
William, just a reminder, we have 2 minutes left. Thanks.
2 minutes before I take questions?
Yes, and we have a couple of questions.
Okay, excellent. So in 2 minutes, these are very preliminary results, but these are things that I'm very excited about. So this is basically what I've talked about so far is building a neural system, which is almost entirely retrieval, okay? But there's been a very new approach to knowledge representation that's come out in the last year or so. It's been shown that very large language models work surprisingly well for basically memorizing factual information. So they work pretty well for answering closed questions. Open book QA is sometimes called. So if you ask a question, Charles Darwin wrote blank, and ask Bert to fill in the blank, you'll get something which is right more often than you think. Now, of course, these also have problems. They're not interpretable, and to update knowledge, to add something new, you have to do completely retrain them. So we've been looking at inserting this sort of neural knowledge representation into a large language model. So we're starting with this system called entities as experts, which I obviously don't have time to talk about too much, but essentially it's got a component which does entity linking, and it has an entity memory. So every entity in its entity vocabulary will be associated with an internal representation, much like a word embedding. And it works pretty well. So this is its performance on a data set called Trivia QA relative to T5, which is a language model that's many, many times larger. So it does quite well on these sorts of factual questions. So the other nice thing about it is there's an easy way of taking this sort of model and extending it. So what we've done is essentially added another type of memory, which is a triple memory. So the transformer can construct a query to this triple memory, which uses the same entity representations for the head and tail as the entity representation. All right, so we're essentially adding something like a follow operation. So this gives you an opportunity to inject new knowledge into the language model. So instead of retraining, you can just add some facts to the triple memory. And this is work with Pat Verga. And this is very new, but there are some exciting results. I'm going to focus on this one right here. This is another knowledge-based question answering system. And what we've done is very carefully constructed a data set where there are trivia questions that have entity answers, all right? And all the information about the facts you need to answer those has been held out, right? So the process is you do some language model training, you do some fine tuning on this data set. We've ablated the data, the fine tuning data and the pre-training data. So you don't have any information about pairs of entities that link a question entity and an answer entity in the test cases. So this red line here is the old entities as expert system. When you go from this normal setting to the zero-shot setting, it's broken, badly broken. Its performance drops a lot, but we can still get some interesting performance in this zero-shot setting. So I'm going to stop here and take questions. There are a couple more slides, which are essentially summary slides, but I think it might be more interesting to take some questions from the audience. So I'm going to stop here.
Yeah, so thanks a lot, William, for the great question, for the great presentation. So the first question we have here is, you have done symbolic methods for KBC, knowledge-based construction, for example, PRA, as well as new neural methods. Have we lost anything by moving to neural methods, or do they strictly dominate?
That's a great question. So do neural models strictly dominate over PRA? So I mean, PRA is not strictly symbolic, right? So in PRA, essentially what you're doing is you're generating a bunch of paths which are weighted, and you're combining them with a weighted classifier. I guess the real question is whether those learning techniques do better or worse than current neural methods. So there haven't actually been a lot of comparisons of Nilau's old PRA system directly to kind of the more recent neural methods. There's probably a chain of comparisons you could follow. So you can get a lot of the power of PRA using a neural approach where essentially what you're doing is using a neural controller to select online the paths. And my guess is those techniques do dominate. They sort of have all the information that PRA has. One thing that they don't dominate with, which I think this talk is sort of trying to get back to a little bit, is interpretability, right? So if you have a neural method which is sort of doing a lot of attention over many different things, and those things may not even have sort of a concrete symbolic meaning, then it's very hard to figure out what they're doing. So I think trying to get back to cases where you can interpret what's happening, where you can sort of like debug, where you can control what's happening is a very important goal going forward.
Yeah, makes sense. Thanks a lot, William. Unfortunately, we are out of time, but there will be a hallway chat session in the evening with all the invited speakers, so please join. There are 2 more questions, so I will forward those to William, and if you are interested, please join at the end of the day. I will now pass it on to Hannah, who will introduce our next invited speaker. Thanks.
Hello, everyone. Thanks for attending the conference. So now let's welcome Jure Leskovic for our second talk. Jure, do you want to present your slides? Thank you. So while Jure starts as a slide, so I just want to introduce him. He's a professor at Stanford and also a chief scientist at Pinterest. Jure's research is at the core of AKBC, mainly machine learning and data mining with graphs, with lots of applications in computer science, data science, health, biomedicine, and so on and so forth. He has received numerous awards, including a Lagrange Prize, a Microsoft Research Faculty Award, a Sloan Fellowship, and also several Best Paper Awards and Test of Time Awards. So it's really our pleasure for us to have Jure accepting our invitation. So please, Jure, you are in charge.
Okay, thank you very much for the invitation and allowing me to give this talk. I know we were planning to be together in I think Riverside, but you know it's also good to give this from my own room. So is this a good way for me to share the presentation? Everyone can see.
Yes.
Yes. Okay, great. So what I want to talk to you about is some recent work we've been doing around a new way to look at knowledge graphs, and in particular to look about inferences and predictions in knowledge graphs. So this will be really about kind of reasoning and doing complex logical queries inside knowledge graphs, but using latest tools from representation learning, embeddings, and so on. So we are interested in knowledge graphs, which for the purpose of this talk, I will just define as these heterogeneous graphs between different types of entities and between having different types of relationships between them. And the way we can think of knowledge graphs is these heterogeneous networks with, as I said, kind of multiple types of entities relations that exist. And the facts are represented through the head relation tail type triples. For example, Alice is a friend with Bob, or Paris is a city, and so on. And we can take all these triples, these facts, and combine them into this large heterogeneous relational structure. And then traditionally, what people have been doing is kind of realizing that these knowledge graphs are often noisy and incomplete, and that one important task in this area is to do knowledge graph completion or link prediction, where basically we want to predict a missing head or a tail of a given triple. So, for example, if we know that Barack Obama was born in the United States, then we may want to infer that his nationality is American or something like that. Right? This is a very simple inference. However, the goal of this talk and what I want to do is kind of, I want to suggest to try to move beyond this kind of simple single link knowledge graph completion and really start thinking about how could we reason over the knowledge graphs using complex logical multi-hop queries. And one way to think about this will be that we are basically doing this kind of complex link prediction on a hypergraph. But let me explain what I mean. So what I mean is that we would like to be able to answer first order logical queries over these knowledge graphs. What I mean by that is we would like to support the existential quantifier, conjunction, disjunction, and negation. So, for example, if a question comes, which in natural language would be, where did all Canadian citizens with Turing Award graduate? Then the logical formula for this query is written here below it. And basically what we are saying is, let's start with a grounded node Turing Award. We want to traverse to some node V over the Wien relation. We would also like to start with a grounded node of Canada and then traverse over the citizen relationship to end up at some node V. And then from there, we would like to go over graduate relationship, and wherever we end up, this is the answer to our query. And the way, as I said, the way we can think of this is that we can think of this as complex link prediction, right? Where basically given the set of grounded entities here on the left, it would be Turing Award and Canada, we'd like to predict a link to all other entities that satisfy our query. So in our case, this would be University of Edinburgh, Cambridge, and McGill, because Hinton and Banjo graduated from these universities. Right? But for example, NYU wouldn't be the answer to our query or wouldn't be part of this hypergraph link that can connect multiple nodes on one end with multiple nodes on the other end. If you look at this carefully, you see that here in this knowledge graph, there is a lot of information missing, and there is no kind of direct path from the grounded nodes, the two on the blue ones on the left, to the answers of the query on the right. So what I mean by this is the way, if the knowledge graph would be complete and we wouldn't be looking at this as a prediction task, then what we would like to do is we'd like to take this query graph and basically use it as a template to match it inside the given knowledge graph. So I could take this, try to match it, and you can see how, for example, this on the bottom left, the bolded arrows, they show parts of the paths relations that actually match to the target graph, right? So from Turing Award, I can go to Hinton, from Canada, I can go to Hinton, and from Hinton, I can go to University of Edinburgh, and that's one answer entity for our question. Another way to look at our query is to think of it with this computation graph, which says, start with the grounded nodes, entities, and then traverse the knowledge graph according to this relationship called Wien, and another one according to the projection or traversal of citizen. Now take the intersection of these two sets of entities. So this will be now all the people who are both Turing Award winners and Canadians, and from that set, take another projection operator, so take another step in the knowledge graph to end up over the graduate relationship to end up at the given answer. And that's one way how we could answer this query if the knowledge graph is complete. However, we would like to see this as a purely prediction task. So basically, we'd like to be able to work in the cases where knowledge graphs are incomplete and noisy and full of kind of unobserved data or unobserved relationships. And the links we'd like to predict in this case are kind of arbitrary because we don't know the query, we don't know the prediction task at the time of training. So we'd like to be able to make predictions or predict these relationships between the grounded nodes and the target entities for an arbitrary logical query. So one approach how we could do this would be to say, let's try to make the knowledge graph complete by doing the traditional knowledge graph completion task. And then, let's try to perhaps assign probabilities to all these relationships. And then let's try to do the template matching the way I explained before. And this would be kind of super unscalable because link prediction would make the entire knowledge graph very noisy and very dense. And then doing this template matching would make everything even worse. So what we would like to do is we would like to use embeddings and relational learning to do this. So what we would like to do is we'd like to do logical operations directly in the embedding space. So rather than to kind of traverse the graph and try to predict each individual missing relation, we just like to take the logical query, represent it as a set of operators, spatial operators in the embedding space, and then do the reasoning directly in the embedding space. And there have been two methods published that are able kind of to do this. The first one had the idea to basically take the query, decompose it into a set of logical operations, represent the query as a single point in the Euclidean space, and then move this point around so that the entities that are answered to the query are close to the embedding of the query. And then query to box, take this idea of box embeddings. So everything is not embedded as a point, but as a box, as a rectangle in high dimensions, so that we can then do intersections over this type of operations. What is challenging here is, in this case, is the curse of dimensionality, right? So if I have my dependency graph here on the top, and then I want to represent this in this kind of box-based algebra, then basically what I'd like to take is this small box of Turing award, learn a projection operator that takes the box and makes it bigger, hopefully covering all the Turing award winners. And then I would like to start with the Canada box and then apply a citizen relationship to it so that it will take this input box and transform it into a bigger box. I can then take the intersection of these two boxes to find Canadians and Turing award winners, and now do another kind of transformation of the box that will hopefully cover all the entities that are the answer to this question. And while this works relatively well, the problem is that it can only handle and and or. So basically, it's easy to see how you can do intersection. You can basically take intersection of boxes. But it's unclear how you could do, for example, negation, because a negation of a box is not a box anymore. So what we would like to do in this talk is we would like to answer arbitrary first order logical queries. So it means, for example, we would like to ask a question: who are the presidents of European countries that never held the football World Cup or the soccer World Cup, if you like, right? So now we would like to do negation as well as and. And if we can do these two, then we can basically also naturally model or, which you can express with and negation. So this is what we will see how we can do. And our approach will be that we want to kind of naturally model negation. So we would like to reason over the kind of the full set of the first order logic. So for this, it is important to be able to model negation. And if we are able to model negation plus conjunction, so and, then we can naturally express or, because A or B can be expressed as not A and not B, as I show here. And again, as I said, if you would want to embed things as boxes, then the problem is that the negation of the box, so basically everything outside the box, is not a box anymore, and your representation of this query basically can get arbitrarily complex, and then it's unclear how to do that. So our idea is that we would like to embed arbitrary first-order logical queries in the embedding space and then do logical operators over this embedding space. And one important characteristic or property for us is that these neural logical operators need to be closed. What we mean by that is that the representation complexity must not increase as the query gets bigger or more complex. Right, so basically we'd like to keep representational complexity fixed while these logical operators can be arbitrarily combined and can remain fixed size regardless of how complex is the query. So that's one thing. Another thing that we'd like to do is we'd like to naturally capture uncertainty of the queries or of the answers to the query. And the last thing we'd like to do is we'd like to be able to reason kind of in this embedding space jointly, in a sense that both entities as well as queries that are kind of arbitrary will both be embedded in this same embedding space. And our insight is to embed entities as well as queries as distributions. And we are going to embed them as beta distributions. And the reason we want to use beta distributions is because they have a fixed domain. They're only defined on an interval 0, 1. And the beta density, as I will show you, is also a very flexible density. So we kind of have a way to approximate negation, right? So we want to embed entities as well as queries as distributions or in this high dimensional embedding space. We would then like to define logical operators that will take beta distributions and transform them. We want to, in particular, support and negation, so not, so that then we can also naturally model. Or we will then also be able to handle uncertainty of queries because we are modeling everything with distributions. So we can measure, for example, entropy and things like that to model uncertainty. And then once we have embedded the query, all we need to do is to check what other entities are nearby, and those will be the answers to our query. So that's generally the idea. Now let me kind of walk you through how we do this. So as I said, we are going to use these probabilistic embeddings that will be basically beta distributions, where along each dimension in the embedding space, we will have an independent beta distribution. So kind of we have independent distributions along the dimensions of the embedding space. Each beta distribution is defined by 2 parameters, alpha and beta. The support of the beta distribution is on the 0, 1 interval, and the beta distribution is very flexible. So here at the bottom, I give you 4 different shapes, just as examples that the beta distribution can take. And you can see this is kind of very, very flexible. So now as a running example, I want to be able to answer this query about who are presidents of European countries that have never hosted a World Cup. And I show you the computation graph here in the middle. And now what we need to do to be able to answer this query is we need to be able to define this probabilistic projection operator that basically will take one beta distribution and transform it such that whatever are the entities on the left, after the transformation, we'll get some new distribution over the entities that will correspond to basically traversing a relationship of a given type in the underlying knowledge graph. Then I want to define a probabilistic or neural intersection operator that will basically take 2 distributions and do an intersection over them. So basically we will have 2 sets of entities, 2 fuzzy sets of entities, and we want to do an intersection. And then we'll also want to do a negation, which will be given a fuzzy set of entities. We want to take a not or a complement of that set. So the way we are going to do this projection operator is that for every relation type in our knowledge graph, we are basically going to learn how to transform this multivariate beta distribution into a new beta distribution. And one way to think of this is that this is basically a traversal from one fuzzy set to another fuzzy set according to a given relation type. And this will just mean that we'll take the density and learn a neural network that will basically transform the parameter values to some new parameter values of the beta distribution, and this way will transform the density or the distribution in our embedding space. For the intersection operator, basically the idea is that we want to take multiple beta distributions and do an intersection over them. And the way we are going to do this is very natural. We are going to take a weighted product of the PDFs of the input beta distributions, right? So if I have two beta distributions on the left and I want to do an AND between them, then I would get the distribution that is on the right. And what is interesting here is that first, the product of beta distributions is still a beta distribution, so this operation is closed. It's commutative, so intersection of distributions Q1 and Q2 is the same as intersection of distributions Q2 and Q1. It is self-consistent, meaning that intersection with yourself gives you an identity, so it doesn't change the distribution, and has this what is called a zero force type behavior, where if I have high probability in one distribution and high probability in the other distribution, the result will be also high probability. But if I'm having high and low, then the probability will be low, or if I have low, it will be low again. And this is what I try to illustrate here, where again we have the red distribution, we have the blue distribution, and the product of the two distribution is green, and you can see how it is high where both distributions take the high value, and it is kind of low where they both take, or one of them takes a low value. So this is how to define intersection operator. So how can you do a negation? It is again kind of a cool insight, is that it's a very natural transformation of the beta distribution, right? So basically, if you take a beta distribution with parameters alpha and beta, and you take 1 over alpha, 1 over beta, then you will basically flip around the distribution. So for example, if you take the distribution on the left, the red one, and apply this negation where you just take 1 over the parameter value, you will get this bimodal distribution on the right. And again, you see that this distribution, wherever the red one takes high values, now the negation takes low values, and the other way around, wherever the red takes low value, the negation will take a high value. Again, what is interesting is that this simple way of defining a negation allows you that negation of a negation is the original distribution as well. So basically, you also get some logical rules or laws of first order logic for free if you do it this way. So now I can quickly walk you through how this would work on this World Cup query that we talked about, right? So basically the way we will do is every entity of the knowledge graph is embedded as a beta distribution. So it's embedded as some kind of density over this embedding space, here illustrated in this kind of two-dimensional sub-projection. So what we would do is we will take these beta distributions, one for the entity Europe, the other one for World Cup. We will apply a transform called located in, or that will give us a distribution, a different distribution over the embedding space that will kind of hopefully that will cover all the countries in Europe. We wanna then do the same thing for the World Cup, that will transform this and give us a distribution over the countries that have held the World Cup. Now we need to apply the negation operator over this, so we'll kind of flip the parameters around the way we discussed, and the distribution will flip around. Now we have the two distributions, and we need to take an AND between them, so an intersection. This is what we do. This is what we do here. Now we basically have a set of countries that are in Europe and have not organized the World Cup. Now we need to do another traversal kind of in the knowledge graph along the president relationship. So it will be another transformation of this multivariate beta distribution. And now we have this distribution in the embedding space. So for example, we can now measure the distance between the embedding of the query here in the middle between let's say the embedding of the president of Portugal versus the president of France. And we can measure, for example, some way of a distance in the embedding space. We are using the KL divergence. And in our case, the Portuguese president would have a low KL divergence to the embedding of the query, while the Macron would have the high KL divergence to the query. Now I showed you how to do AND and how to do negation. The question is, how could we do disjunction? How can we do OR? And there are two options to do this. One is that comes from the observation that any logical formula can be rewritten into what is called disjunctive normal form. So basically, we can rewrite it into a disjunction of conjunctions. And this is useful because if we are able to answer queries with conjunctions, then we can just answer each conjunctive query separately. And then the final answer is kind of the union of these individual query answers. This is great because now we have a very expressive way to handle disjunction. However, this can be computationally expensive because rewriting the query may increase the query size exponentially in the worst case. Another option is to use De Morgan laws, which would basically say you basically rewrite OR as a double negation of an AND, as I show you here. This means that now the execution time will stay constant or linear with the query size, but this will be a bit less expressive or a bit less powerful because we are modeling union simply as a AND and with AND and NOT. And then the last thing that is interesting and that we can do is the question, can we naturally also model uncertainty? Which in our case would be, can we draw in some sense a connection between the entropy of the beta distribution and the number of answers the query has, so number of answer entities. And the idea would be that the more answer entities we have, the more uncertain we are about each of them. So we would like the entropy of our beta distribution to be higher for queries that have a lot of different answers. And I will show you an experiment later that will show that actually we get very good estimate of this without really incorporating it in the training anywhere. So the benefits will be that we have now a very scalable and efficient method for answering any first order logic based query. And at the end, all we need to be able to do is do k nearest neighbors in high dimensions. This is very general because our operators can be kind of combined, chained in arbitrary ways where the representational complexity won't increase. And as I will show you, this is very robust to noise in a sense that we can really do, in some sense, arbitrary hyperlink prediction over any kind of prediction rule, which we here call a query. The way we train this is that we basically generate synthetic queries. And then with every query, we have a set of positive entities and a set of negative entities. This would be entities that are answer to our query. Negatives would be entities that are not answer to the query, but are of correct answer type. So if the answer to the query is a human, then other humans who are not answer to the query would be negative examples. And then based on this, we can basically learn our model, which means we need to learn the embeddings of all the entities, as well as this projection, intersection, and negation operators. And that's basically it. Our experimental setup is focused on the following questions. Does our method generalize to new unseen queries? Does it generalize to new unseen logical query structures? And whether we can model uncertainty. And as I said, our evaluation will basically be a link prediction evaluation. So we will train on an incomplete knowledge graph. And then we will only test on the queries that are not answerable in the training graph. What I mean is that every test query will have at least one edge missing. So we cannot simply traverse the query graph to answer the query, but we have to implicitly input the missing edges in order to identify the answers. So we are really doing this kind of, in some sense, link prediction in a hypergraph. That's the best way to think of this. We are doing this over 3 different knowledge graphs, Freebase 15K, 15K 237, and then also on the NEL knowledge graph from Carnegie Mellon University. We will have a set of training query structures, which you can see here. These are path queries, these are intersection queries, as well as queries that are kind of intersections, as well as negations. And then we are also going to evaluate on queries or query structures that we never see during training. Notice that these are different logical structures that the method does not see during training. What we find is that our method here called beta E significantly outperforms previous methods on conjunctive queries only. So these are queries that don't contain negation, because prior methods cannot handle queries with negation. So this is what we see here on the left. These are the kind of training queries, or these are logical structures that are the same as in the training data, but of course relations are different in the test set than they are in the training set. Then we also evaluate on logical structures that the method has not seen during training at all. And we have 2 ways how to model union with the De Morgan laws. This is DM, and the disjunctive normal form. And you see how disjunctive normal form tends to perform better. On average, we get about 18–15% improvement over query to box in terms of hits at once. So in terms of predicting the link between the starting entities and the target answer entity, where there is at least one edge missing along the path of the query. We can also do things. Yes.
Sorry to interrupt you. So we have about 2 minutes before questions.
Don't we have 5?
5 minutes, but like 9:30, including questions.
I see. I thought we started a bit late, but that's okay. I will finish. So this is negation. It works great as well. And we can also model uncertainty, as I said, where we can measure correlation between the basically the entropy of the beta distribution and the number of answers the query has. And we are getting much better modeling of uncertainty than what previous methods are able to do. So let me conclude. So what I presented is this notion of beta embeddings for answering logical queries or arbitrary logical queries in incomplete and noisy knowledge graphs. We can handle the first order logic, so means existential quantifier and negation. We can generalize to unseen queries, novel logical structures. We can naturally model query uncertainty. And the future work is really about how can we further push this and see whether there are even better ideas how to model uncertainties, how to define logical operators in the embedding space. And in the last 1 minute, I just want to say one more thing, is that as people who are working with machine learning on graphs, we are realizing that we are lacking a diverse, challenging, and realistic benchmark data sets for machine learning with graphs and knowledge graphs in particular. So we have developed a consortium and a working group called Open Graph Benchmark, where our goal is to release, or we have already released, a set of benchmarks for machine learning with graphs, with data sets, the code base to load, construct, and represent graphs, as well as performance metric evaluation, so that model evaluation and comparison can be done very quickly, and the research can proceed quickly. We have different types of tasks at level of nodes, links, and graphs, different domains, including knowledge graphs, and different sizes from small, which is basically what fits into a single GPU, to medium and large, that provide a bit more challenges. If you are interested, please check ogb.stanford.edu. So with this, I'm done with my talk, and thank you very much.
Thanks, Jure. That was a great talk. So people are asking how to applaud. So we don't know how to applaud virtually. So we have a lot of questions. I tried to ask them according to the votes that each of them got. So first question, how do you translate the natural language question to first order logic form?
Yes, great question. That's not what our work starts with the, sorry if I was not clear, but our work starts with the query graph given. So I kind of assume that the query graph is being given to us. I give it in the natural language because it's easier, but basically the way our work starts is that we get this dependency graph and we start from there. Sorry if that was not clear, but yeah, that's a great question.
Second question, Andrew Su asks, in the abstraction of entities from points to distributions, what are the implications for the size of the training set that is required?
You are saying because now our embeddings might be more may require more parameters. It is actually like at the end, our embedding dimensionality is increasing by a factor of 2, right? Rather than having one coordinate along each dimension, now we have an alpha and beta along each dimension. So the blow up is not huge. And we actually, when we run comparisons, we give all methods the same amount of free parameters. So the methods that are embedding into dots, into points, we give them twice the embedding dimensionality. So we don't get any explosion. So it is not an issue.
Got it. So one more question. The disjunction of two betas should be multimodal, but your use of De Morgan to capture disjunction doesn't result in a multimodal shape. Approximation regrets?
Yes, so this is, I think, yes, that's a good point. What we are able to do is we can basically, when we flip the beta distribution around, we get from unimodal to bimodal. It would be interesting to see, and obviously we cannot model, we could not model along a single dimension multiple modes. That is a correct observation. And of course, I think then it becomes a good question, at what complexity of the query will this approximation start to break down? Basically, I think the point is the following. There is a lot of impossibility theorems that one can prove around here. But if we try to be constructive and say what is possible and what kind of works well in practice, this is more what we were guided towards.
So I can ask the last question, which is, how do we represent entity hierarchy? Like a car is a vehicle.
Yes, that's good. So for entity hierarchies, one idea is how you can represent this. It is very natural to represent hierarchies in with boxes, because you can make them smaller and contained. You could also imagine that you could do something similar with distributions, where you take the more fine-grained concept and put it below in some sense. Another good way to capture hierarchies is hyperbolic space. So we are actually right now looking into hyperbolic geometry, because there you can very naturally and very faithfully capture hierarchies. So that's one of the pieces of work that we are currently focusing on.
Thanks, Jure. I think we are over time. We still have more questions, but please come to the hallway sessions.
Yes, I will be half hour late to that session because I'm giving another talk. So I'll be half hour late, but I will show up and very happy to answer any questions people might have.
Awesome. And I'll email you the rest of questions.
Thank you very much. Thank you, guys.
Thank you. And now we're gonna be listening to the live talks for the spotlight papers.
Yeah, so I'm going to share this video. I'm just going to play it. These are also on the paper pages, but we'll have the 5 spotlight talks. They're all about 10 minutes each, one after the other one. All right, this is the first one.
Hello, everyone. I am Fabio Petroni from Facebook AI Research. And in this talk, I will present how context affects language models' factual predictions. A joint work between Facebook AI Research and NLP Lab at UCL. At EMNLP last year, in this paper, we show that language models are able to store and retrieve factual knowledge to some extent. And we created the Llama probe to do this kind of analysis. That is a collection of closed-style questions with a single token answer. And here you can see an example. The theory of relativity was developed by Musk. And we asked BERT to fill the mask. And in this particular case, it predicts Einstein. That is a correct prediction. But storing factual knowledge in a fixed number of weights has clearly limitations. So for this other example, Giacomo Tedesco plays in Musk position. BERT gets it wrong. Also, as humans, we don't always have the answer in our memory, in our parameters, but we heavily rely on external knowledge, for instance, from Wikipedia. So we can go in Wikipedia, look at the Giacomo Tedesco Wikipedia page, and see that he is a midfielder. The idea of this paper is to integrate additional contextual information into BERT in order to study its behavior. In particular, we consider 4 types of contexts: oracle, retrieved, generated, and adversarial. For oracle context, we use the one provided in Llama that often contains the true answer. For retrieved context, we use the information retrieval system of Dr. QA to retrieve relevant information for the question. And as generated context, we use the generation of an autoregressive language model. And this allows us to test the performance of a solution completely based on knowledge inside the parameters of a neural model. But note that the generation might not be related to the question and also might not be factual. Finally, we test the performance of BERT against adversarial context by randomly sampling oracle context from different questions that has the same relation. And note that adversarial context always contains a distracting and semantically plausible answer. Let me show you some results. In this table, you can see the precision at 1 for BERT, that is the percentage of time it gets the answer correct for the Google RE, T-Rex, and Squad datasets in Llama. And when we consider oracle context in input together with the question, we have a dramatic improvement in performance for BERT on the Llama probe. And this result shows the unsupervised machine reading capabilities of pre-trained language models that are able to copy the answer from the context into the masked position. Moreover, when we consider the performance of BERT plus an information retrieval system, we observe that it basically matched the performance of a supervised baseline. In this particular case, we use Dr. QA by translating each closed-style question into another questions. And this is, let's say, really impressive, given that BERT didn't get any supervision at all for this task. When we consider the generated context, we have a slightly drop in performance. While when we consider adversarial context, the performance are more or less the same with no context or adversarial context. And these results really surprised us at the beginning. And we were not sure why this was the case, or why BERT didn't get confused at all by adversarial context. But then we looked into the next sentence prediction pre-training task of BERT, and we found the answer. So BERT was trained both with masked language model, but also to understand if the second segment is a valid continuation of the first segment. So in this particular case, we mapped the question as the first segment and the context as the second segment. So we noticed that if the context is relevant, the next sentence prediction classifier always outputs a 1, and the BERT looks at the context in order to do its prediction. But when the context is not relevant, for instance, as in the case of the adversarial context, we have that the next sentence prediction classifier predicts a 0, and BERT does not look at that context. So it's affected by the next sentence prediction output, and the prediction in this case is equivalent to the 0 context prediction. In this plot, you can see the change in precision at 1 relative to the 0 context. And for BERT, using a single segment or 2 segments, so enabling the next sentence prediction ability. And also for Roberta, note that Roberta has been trained without the next sentence prediction feature, but it has the option to divide the input into sentences by using a end of sentence token. And from this bar plot, you can see that the best performance both in the adversarial case and the oracle case are achieved by using 2 segments, so with the next sentence prediction task. And by using a single segment, the adversarial context completely ruins the performance. And for Roberto, we have a similar behavior, but is not as robust as BERT. Moreover, we notice that the more relevant that BERT thinks the context is, the more we see an increase in the likelihood of the 2 answers. So BERT heavily relies on the next sentence prediction to actually decide to attend or not over the other piece, over the other segment, to do a prediction in a segment. This table shows the percentage of time that BERT changes its output for the better or the worst. You can see, for instance, that when using oracle context, it changed prediction 34% of the time for the better, and 7% of the time when the context is generated by a language model. So this shows that autoregressive language models can actually generate relevant context sometimes and potentially serve as unsupervised information retrieval systems. However, BERT is completely unable to filter generated irrelevant or factually wrong information because he always thinks that the generation is a plausible continuation of the question. So here you can see an example. So for the same example as before, the generated context was how much does he play? He can play fullback, wing, or center. He can also play, and the next sentence prediction score is 1. For this reason, BERT copies the wrong answer from the context that is full. Here is a final example for retrieved context. And it's quite interesting because even though the answer is not in the context, BERT was able to combine this retrieved information with its own internal representation of knowledge to come out with the correct answer. To conclude, I think we should reconsider the next sentence prediction task because we show that it is an important component for robust exploitation of retrieved context. I also want to point out that the comparison with Dr. QA is not 100% fair because Dr. QA is an extractive solution while BERT is an abstractive, and also the single token limitation of the Llama probe is an advantage for BERT. Nevertheless, this work, together with a large body of literature in recent years, show that flexible and powerful unsupervised QA systems might not be too far on the horizon. Thank you everyone for your attention. If you want to follow our works and updates, you can follow me on Twitter or you can follow any other among the authors. Thank you.
was my try. Applause. And here's the next talk.
Well, hello everyone. I am Priya from UC Irvine. And I hope you're doing great in the age of COVID-19. Also, the past couple of months has shown that there are many things that are much more important than knowledge graph. But today I'm going to talk about revisiting evaluation of knowledge-based completion models. This is joined for by me, Yifan Tian, and my advisor, Professor Samir Singh. I'm going to start my talk by giving a brief introduction on knowledge graph completion. Then I'm going to share the shortcoming that we find for the current evaluation protocols. And finally, I'm going to provide the solution that we find for these shortcomings, which is introducing Yago 3TC benchmark. Let's start with knowledge graph completion overview. Knowledge graphs are representation of information in the form of a graph where nodes represent entities and edges represent the relation between entities. Knowledge graph usually created through several sources of information, such as unstructured text, structured text, and images. Because of the way these knowledge graphs are being created, there are many missing information inside them, resulting in creation of knowledge graph completion task. Here, the goal is to identify missing information using all kinds of other information that we have in the graph. For example, knowing that Barack Obama is married to Michelle and Frederick Barack has a daughter named Sasha, our goal is to being able to predict that Michelle has a daughter named Sasha as well. Further, since we don't know the non-existent links are true or false, we force to adopt ranking metrics as an evaluation measure. While in real-world application, mostly we want to know whether information is true or false, and we don't care about the ranking. More specifically, there are two fundamental approaches to evaluate these knowledge graph completion model. The first one is the ranking metrics, which try to rank the subject or object of the target triple in comparison to the pool of all possible entities, which again doesn't correspond to real-world use case in many instances. And further, triple classification, which try to classify each triple as true or false by learning a threshold for each relation using the validation data. By that, I think we are ready to move on to discuss about the actual shortcoming. But before diving into the details, I want to lay out the three negative sampling approach that we consider in this work. The first one is random sampling, which is widely adopted, and replace the subject or object by a random entity from the pool of all possible entities. The second sampling that we consider is the constraint sampling, which first filter all the entities that at least appear once with the relation of target triple. Then we replace the subject or object with a random entity from this specific subset. Finally, we consider careful sampling, which first identify all the entities that never appear with the relation of target triple, and then replace the subject or object with the highest score entity using a knowledge graph completion model. In this presentation, I'm going to talk only about three issues that we find in the current evaluation approaches. I'm going to start with the calibration. We observe that calibration study is not well defined for these knowledge graph completion models. More specifically, in Yago 3 data for three models of Tucker, Rotati, and D-Smalls, which were state-of-the-art results at the time that we conduct this experiment, we see none of these plots are actually calibrated, and they are very under confidence. The red lines is the ideal model that we are looking for. We see similar performance for constant sampling and as well careful sampling as well. And there are 2 points in this plot. Firstly, most of these plots are not calibrated at all. Secondly, we see as we make the negative sampling more challenging, the behavior of each model become completely different, and demonstrating that the ambiguous nature of calibration study for these knowledge graph completion models. The second issue that we observed was the existence of semi-inverse relations in knowledge graph. More specifically, we observed that in WordNet 18RR, there are 4 specific relations that whenever we see them in the train data with a high possibility, we see the same triple with the same component, but with the reverse relation as well. These relations consist 40% of train data and 30% of the test data, resulting in a very high performance of 0.9 MRR on these triples. Similarly, at Yago 3.10, we observed that whenever we see, in 80% of the time that we see a relation placed for between 2 entities, we see relation is affiliated to between those 2 entities as well. These relations consist around 55% of train data and 50% of test data, again resulting on very high MRR performance. The problem with these relations is the fact that since they are very simple to predict and they appear a lot in the knowledge graph, they result in ranking it not being able to reflect design power properly. Finally, I'm going to talk about the triple classification robustness. Here we see the accuracy of this classifier on tree-based WordNet and Yago tree. We observed that when we train this classifier using conventional way, but change the negative sampling in the inference time, the accuracy dropped dramatically, demonstrating that these classifiers are very brittle. I just want to point out that the current trivial classification results is naively around 90% as we see in this graph. Now the question that remains is how we can resolve this issue. We are looking for benchmarks that aligns with real-world application goals and further can properly differentiate between these knowledge graph completion models, and finally can capture reasoning powers of these models. And the challenge that we are facing to come up with such benchmarks is basically the fact that knowledge graphs are not complete. There are many, many non-existent links in them, and identifying any labels for each fact is very hard and expensive. The solution that we came up with for all of these challenges issue was Yago 3TC benchmark, which we created by firstly select a random subset from Yago 3 test data. Then we identified top scoring triple from for each one of these target triple using a knowledge graph completion models. And then we filtered these triples using several rules guaranteeing the factuality of each one of them. And finally, we get the labels for remaining triple using our crowdsourcing pipeline. In our crowdsourcing pipeline, after identifying top scoring triple for each target fact, we passed them through our first round of crowdsourcing with 3 participants. If just one of them think a triple is positive, we pass that specific triple through a second round of annotation with 2 participants. This time, if both of the annotators agree that the triple is positive, we accept the label. Going through our crowdsourcing pipeline, we could gather around 30,000 triples, from which around 10% of them has positive label. Now let's see the evaluation result on Yago 3TC benchmark. We first consider triple classification. In this experiment, we consider another baseline, named as type C, where as our classifier, we simply check whether the subject and object of target triple match with the relation type using training data. As we can see in the figure, these simple baselines perform very similarly to a state-of-the-art result models, casting doubt on the whole progress that we have so far on the knowledge graph completion models. In the paper, we tried to come up with several measures to improve the performance of these models, but we are far from the acceptable performance. We further see a huge drop in accuracy in this plot compared to the previous result that we have, which was around 90%, which we believe is capturing the power of these models more realistic. We further conduct experiment on calibration. As we can see in this figure, there is 2 points here. Firstly, we see the order of models is reverse here, having the Tucker as the most calibrated model right now. And further, we observe that now all of the models are overconfident compared to previous results that were underconfident, which consistent with the previous calibration study on neural network models. Through this talk, we first observed that ranking metrics are not very trustworthy. We further noticed that triple classification is not robust, and these evaluation metrics do not align with real-world application goal, resulting in creation of Yago 3TC benchmark as the first step toward better evaluating these knowledge graph completion models. As a final note, I just want to mention that we intend to create a web-hosted evaluation platform to continuously update Yago 3TC using new knowledge graph completion models. In this talk, I had a chance to go through all of these topics, and you can see the website for our project and my contact information here. Thank you for your time.
Hi, my name is Aida. I'm a PhD student at the University of Washington, working with Professor Hannah Haji-Shirzi We want to welcome you to the virtual presentation of our work on procedural reading comprehension, and also thank our co-authors, Antoine, Bahavna, and Yajin. We refer to process as sequence of events describing changes in the properties of the main elements that are participating in the process. Procedural text describing the process can be found in various domains, for example, the cooking recipe or the scientific process or a mathematical problem can all be seen as procedural text. To give an example, here is the procedural text describing a scientific process. We want to illustrate how we can map from text to find the location attributes of the entities, fuel, and mechanical energy throughout the process. By going through the first sentence, the engine must be powered by gas or some fuel source. The reader can easily infer that the location of the fuel is now engine. But looking at the second sentence, the fuel source will power an alternator poses new challenges as we see that there is a change in mechanical energy, but the entity term is not explicitly mentioned, and the reader should refer to the word power to infer that there is a new type of energy that is getting created. We are also interested in looking at the transitions that are happening from one time point to another in the attribute values, and we refer to them as transitions. The problem of procedural reading comprehension is a problem defined as given the input of procedural text and the list of entities, we want to track the attribute and transition values of those entities throughout the process at every time point. By doing so, we can answer high-level questions, for example, what is happening to the fuel? And by looking at the table, we can easily infer that it's getting converted to mechanical energy through an alternator. Procedural reading comprehension task poses new challenges. The main source of the challenge is due to the difference in nature of dynamic text versus static text. The entities are changing. There might be implicit mentions of entities or the attribute changes. For example, if you look at the sentence 2, there is no mention of mechanical energy or the fact that, or explicit mention that the fuel is getting destroyed. Also, the other challenge is due to the fact that we want to predict attribute values as spans of text instead of predefined classes, which gives the model more ability to generalize beyond what we can predefine for the problem. In this paper, we introduce new formalism for modeling procedural reading comprehension text. Each procedure is mapped to entities, attributes, and transitions. We also introduce DynaPro, a neural reading comprehension model that jointly predicts attributes and transitions. The attributes here are predicted either as spans of text or predefined classes. We also show that our model achieves the state of the art, and we provide a multiple analysis. Our model, DynaPro, leverages reading comprehension with inputting the entity over context. The model predicts the attribute values either as predefined classes or spans of text. The model is trained end-to-end to optimize the prediction for predicting attribute and transition loss. And the output of the model are both attributes and transitions that are predicted over time. Let's start with how we can construct an input given process which contains a list of sentences, each individually describing an event, and the entity and the attribute that we want to track. We want to create an input for time step k and for entity 0. The first step is to ask a query about the entity and the location. If the location is the query about entity and attributes. If the attribute is location, we can ask where is the entity. Also, if we want to ask up to time point k, we truncated the process up to time point k, and we only include those sentences. We also include notations of predefined classes to have potential attribute classes present as the span of text. After constructing this input, the input is passed through contextual embedding unit in order to get entity-aware representation. Here, the contextual embedding unit we use is the BERT embeddings. The entity-aware representation is then used for predicting attributes as predefined classes or strands of text. The predefined classes in our situations are a nowhere, somewhere, or span of text. With the attribute predictions, we move to create attribute-aware representation. The intuition is to rescale the original entity-aware representation based on the probability distribution of the attribute predictions for previous and current time step in order to capture the change. The entity-aware representation and attribute-aware representation then pass to the transition prediction module, which classifies over 4 different classes: destroy, move, create, and no transition. In order to have smoother predictions, we use a BiLSTM layer in order to have a memory of what are the previous predictions. As for the experiments, for our main benchmark, we use ProPara dataset. ProPara is a carefully annotated data containing around 400 scientific paragraphs for the training set. Over the ProPara, there are multiple test beds and benchmarks introduced. The sentence level task asks about each prediction individually, if the transition is predicted, when and where it's predicted. The document level task also asks about the high level questions over the whole process. For example, it asks about the input, the output, or what are the conversions. The action dependency test asks if the transition that is predicted has further influence on the next predictions. As you can see in the chart, our model DynaPro achieves a state-of-the-art over these benchmarks. We also did ablation study in order to measure the impact of the different components of our model. We observed that the joint prediction of transition and attributes is helpful by removing that this variation doesn't has lower performance than the original DynaPro. In order to measure the impact of attribute-aware representation, we did 2 experiments by removing the attribute-aware representation or replacing that with a classification token that is provided by BERT. And we see that both of these variation has lower performance than the DynaPro. We also showed the impact of truncating the input by feeding the full context and observing that the results are much lower. We also did qualitative analysis over our predictions, and we categorized our errors into 3 main categories. The first category of problems is due to incorrect class prediction. We observed that in most cases, our model tries to predict unknown location instead of predicting unknown. Our model is trying to push for span. We also observed that there are incorrect span predictions. For example, in the example, we have to predict heart, whereas our model predicts right side of your heart. The third category of the problems are due to inconsistent transitions. We observe that as we build the tables incrementally, there are some transitions that are attempting to create entities that are already exist, moving entities that are destroyed, or destroying entities that are already destroyed. And these are the root of some inconsistency and errors. To summarize, we present a general formalism for modeling procedural reading comprehension task. We introduced DynaPro, a neural model that is trained end-to-end to predict attributes and transitions. We also show that our model achieves state-of-the-art and over procedural reading comprehension task. Finally, thanks for listening to our talk. Hi, my name is Aida. I'm a PhD student at the University of Washington, working with Professor.
Hello, everyone. I'm Jen. It's my pleasure today to present a joint work with Yinghu Ma, Yu Wang, Stefan Günnemann, and Falk Tusk. In this work, we focus on learning from temporal knowledge graphs, where we use a graph-Hawkes process to capture the underlying dynamics. Compared to semantic knowledge graphs, temporal knowledge graphs, or TKG for short, store time-dependent events instead of set facts. For example, the GDLT dataset extracts news from newsletters and uses the key information such as quadruple of subject, predicate, object, and timestamp to represent an event. Here is a graph view of a temporal knowledge graph, where nodes correspond to entities, and an edge corresponds to a predicate with a timestamp indicating when this event happened. Since each labeled edge represents an event, we can consider a temporal knowledge graph as a sequence of events, where edges with the same timestamp are considered as concurrent events. For example, there are 5 edges in the first graph slice. We have then 5 concurrent events at the timestamp T1, so on and so forth. Based on observed events, our task is to predict lengths in a future time instance. For example, T4 here. There are several tools for modeling event sequences, such as the Hawkes process, which is a self-exciting point process. Each event type K has a time-varying intensity that represents the expected number of occurrences of this event in a unit time interval. In the Hawkes process, past events conspire to temporarily raise the intensity of future events. Wang and Eisner generalized the Hawkes process by using a concurrent neural network to predict the intensity function called the neural Hawkes process. In the neural Hawkes process, an intensity function jumps discontinuously with each new event and then drifts toward a base intensity. An occurred event can not only raise but also reduce the intensities. Therefore, the model can capture both the excitation and inhibition effects. Although the event time in existing temporal knowledge graphs, such as GDLT, is discretized, we use the Hawkes process to model discrete events in continuous time. The advantage is that we can predict continuous time when events happen. However, we can't directly apply the Hawkes process on temporal knowledge graph due to the scalability issue. More specifically, each possible link between 2 nodes represents an event type, namely a triple of subject object. The number of probable event types of knowledge graph is enormous. For example, there are 1.4 times 10 to the power of 10 probable event types in our dataset, while the training set only contains about 10 to the power of 6 existing event types. So the graph is very sparse. By addressing this issue, we developed a graph-Hawkes neural network, or GHN for short, that can be applied to large-scale temporal knowledge graphs. In the following, I will take this object prediction query as an example to explain our model. Inspired by the score function of static knowledge graph embedding methods, we use entity and predicate representations to model intensity functions instead of using event-specific parameters. Besides, we focus on the influence of past events that include the query subject E1 and the query predicate P1. We call these events the historical event sequence of this query. By predicting the missing objects, we fit this historical event sequence into an RNN and compute the intensity function. But the model can still capture information from other events because there are shared values for entities and predicates. Modeling the intensity function using entity and predicate-specific parameters and narrowing the scope of past events enable our approach to deal with large-scale temporal knowledge graphs. Continuing with this query, the right figure shows that the subject entity E1 form 2 links with other object entities at the timestamp T1. To summarize these concurrent events, we introduce a neighborhood aggregation module that computes the mean of the object embeddings, where the big O represents the set of entity 3 and entity 4. Then we define an intensity function to characterize the Graph-Hawkes process. First, we feed the historic event sequence into the neighborhood aggregation module, and then feed the results into a continuous time LSTM. After the CLSTM processes all events in the historic event sequence, we concatenate the hidden state vector with the subject embedding and the predicate embedding. And then we make an inner product between this output and embedding of an object candidate as a similarity measure. Especially for this object prediction query, we refer to this intensity function as the subject-centric intensity function for predicting the missing object. For an object prediction query, we choose the object candidate with the highest intensity at the prediction. We consider the link prediction task as a multi-class classification task where each class corresponds to an entity candidate. For the time prediction task, given an event type, we aim to predict its next occurrence time. We compute the probability density that a given triple occurs at time t according to the survival analysis theory. Then we calculate the expectation of the next event time based on the density function, where we use the trapezoidal rule to estimate the integral. We evaluate our model on two benchmark datasets, the GDLT and the SEWS14 datasets, where the first one contains about 2 million quadruples. Table 1 summarizes link prediction results on both datasets. We see that our approach outperforms all other baseline models. Different from the baseline models with discrete state spaces, we model the probability of an event in continuous time. Therefore, our approach can compute the event probability at an arbitrary time stamp, which enhances our model's expressiveness. For the time prediction task, we propose a plausible way to evaluate time prediction performance considering concurrent events. Otherwise, most branches value would be 0, as in a baseline model called no-evolve. We compare our approach with LITSWE and no-evolve, since only these two models are capable of performing the time prediction task on temporal notch graphs. The figures demonstrate that our approach achieves competitive results on both datasets. There are several use cases of our approach. First, combining a data space of political events, we can develop a system to provide conflict early warnings. Besides, we can construct a temporal notch graph that stores healthy records of individual patients and apply our approach for risk assessment of patients. To summarize, we propose the Graph-Hawkes neural network for forecasting on large-scale temporal notch graphs. We solved the challenge of massive event types, borrowing the ideas of the score function from static notch graphs. Also, we define a plausible way to evaluate the time prediction and the new metrics on temporal notch graph modeling. There are a few interesting future directions, such as enabling induction on new nodes and developing explainable approaches for the link prediction task. Thank you for your attention. If you are interested, please check our paper for more details.
Hello, everyone. Today, I'm going to introduce a new, simple, and effective technique for reasoning in knowledge bases, in which the reasoning rules required to answer a query about an entity are derived dynamically from other entities in the knowledge base. Our approach is simple, requires no training, and is reminiscent of case-based reasoning in classical AI. I'm Rajorshi, and this is a joint work with Ameya Kotbole, Shahzad Dhuliawala, Manzil Zahiri, and my advisor, Professor Andrew McCall. Automated reasoning is defined as the ability of computing systems to infer new facts from observed evidence. We are interested in automated reasoning over large knowledge bases with rich and diverse semantic types. Knowledge bases provide an excellent testbed for automated reasoning. And here's why. The first step in creating a knowledge base is to gather a lot of text and identify the entities present in them, followed by connecting them with semantic relations. This figure represents a toy knowledge graph in which the entities are nodes in the graph represented in colorful rectangles, and the relations are represented as labeled edges. Even in this toy knowledge graph, we can infer several unobserved facts. For example, we can infer that Andrew lives in the United States by doing compositional reasoning on the observed facts that he works at UMass, which is located in Amherst, which is located in the US. Or the fact that I work at UMass because I'm a graduate student working with Andrew, who works at UMass. There has been an array of work which learns this logical inference rule from data and stores them in the model parameters. This paper, we argue that reasoning can also be very contextual, and the reasoning rules required to answer a query can heavily depend on the entities present in the query. For example, consider the following query, which is always there in every graduate student's mind when they're getting ready to travel to a conference. Do I need visa for traveling to AKBC 2021? This translates to the following knowledge base query. Now, to answer this question, it would really depend on the type of passport I hold. For example, do I have a diplomat passport or not? Or the list of countries which offer visa on arrival to Indian citizens or the current political allies of India. Note, the reasoning rules would be different for other people. For example, it would be really different for Andrew. Moreover, the rules to answer this question are dynamic in nature because they inherently depend on the foreign policy of a country, which keeps changing with time. In a nutshell, to answer such queries, need different fine-grained rule for each entity, and hence it becomes hard to store all of them in the model parameters. Also, it's unclear how the parametric models will adapt when the underlying data changes. The contributions of this work is to develop an approach which learn fine-grained rules tailored for each entity by deriving logical rules dynamically from other similar or contextual entities rather than storing them in parameters. In fact, other than the entity embeddings, our model has no parameters. And since the rules are derived at inference time for each entity, it can handle updates or changes to data seamlessly. First, a small primer on case-based reasoning. CBR is described as a process of solving new problems based on solution to similar past problems. For example, consider an auto mechanic trying to fix a car by recollecting past memories of them solving other cars with similar problems. A case is an abstract representation of a past problem and its solution. CBR is a four-step process. The first step is retrieving the relevant cases from memory given a new problem, followed by trying to reuse the solutions to previous cases. However, sometimes the solution might not work out of the box. In that case, the solution should be revised accordingly. If the revised solution works, then the new case is added back to the memory. How do we represent a case in our knowledge base setting? For each fact in the knowledge graph, we connect a random sample of paths which connect the two entities in the fact. So a case is represented as a pair of the fact and a random sample of paths up to a certain length, connecting the entities in the fact. We repeat this process for every fact in the knowledge graph, and thus we have case memory. Now, for a new query, we retrieve k-relevant cases from memory. This is followed by gathering the paths from those cases and then removing the entities so that these paths are now just a sequence of relation types. This is followed by sorting them with respect to frequency. Next, for each path, we symbolically match them to paths in the neighborhood of the query entity. Note how the first two paths get matched, but the last two don't, because these paths don't exist in the neighborhood of the query entity. Lastly, the entities which are at the end of paths are returned as answers. Our model represents entities as a sparse vector of its neighborhood relations. This is a very simple way of representing an entity, but it can be easily extended, for example, to include entity information in the neighborhood, or can be replaced by dense embeddings from trained neural models. Apart from these sparse entities, our model requires no other parameters and does not require any training. The similarity is the cosine similarity between entities, and for a given query, we consider only those entities for which we observe the query relation. Coming to the experiments, our task is knowledge-based completion, in which we predict the head or tail entities. Given an unobserved triple, we test our model on 3 academic knowledge graphs. And our baselines are several state-of-the-art parametric rule learning or embedding-based methods. On the net dataset, our approach outperforms all other rule learning or embedding-based approaches, gaining over more than 3 points in accuracy. On the WordNet dataset, our approach performs competitively with all rule learning and embedding-based approaches, except for the newly proposed rotate model. And on the subset of freebase, we not only outperform embedding and rule learning approaches, but we also outperform approaches which observe the logical rules required during training. Lastly, we find that our method is able to gather more fine-grained rules for every query type in the nil dataset when compared to Minerva, which is an existing rule learning approach. Please refer to the paper for other experiments on low data settings and even more analysis. We introduce a general framework with a lot of exciting future directions. For example, learning richer entity representation and a better similarity metric, better matching of paths, improving upon our simple symbolic matches, and considering subgraph instead of paths as solution to cases. In conclusion, we introduce a new approach that derives reasoning rule dynamically for each entity and requires no training and outperforms existing rule induction methods and are comparable to existing embedding-based approaches. Our methods have a lot of exciting future directions. Thank you.
All right, thank you everyone. So we're going to be doing poster sessions right now. There should be Zoom meetings available for each posters of the 5 posters. Go in, let's chat there. Yeah, and we'll be back in about an hour or the invited talk by Jamie Taylor from Google.
Nice to meet you, Jamie.
All right, we're going to get started again. Jamie, if you could start presenting your slides, that would be good while I introduce you. I'm pleased to introduce Jamie Taylor, who is coming up on 10 years now at Google, where he manages the schema team for Google's Knowledge Graph. He joined Google following the acquisition of MetaWeb, where he was the Minister of Information, helping to organize data in Freebase. Prior to that, he published a book on programming the semantic web and was the CTO of Determined Software. Jamie, welcome to AKBC.
Thank you so much. I'm honored to be here and to be invited to this conference. So for those that know me, it's, I think, perhaps a bit amusing that I've been invited to a conference, to talk at a conference on automated knowledge-based construction. Because both in the world that I work and my own background, I actually don't know anything about the automated side of this. The world that I work in is far from automated. We have automated processes and things like that, but in terms of the knowledge-based construction, the world that I work in is really one of watchmaker precision semantics. And you can imagine people putting very tight gearings together to make very fine-grained timepieces. And I feel as though that's essentially the world that I work in. We're dealing with the very sort of tight integration of entities along very fine-grained semantic lines. And so when I talk about the knowledge graph, this is Google's knowledge graph, and I am coming up on 10 years of working on it. The knowledge graph grew from Freebase and was a part of the MetaWeb acquisition. And so the knowledge base that I work on has been the same knowledge base for 14 years. And in its truth, maintenance and things like that is very long and enduring. And so literally the first assertions that went into Freebase are still the core of Google's knowledge graph, even though the scale at which we're working now is much larger than most people can appreciate. We have about 5 billion entities that we're dealing with, and about 500 billion facts about those entities. So what I'd like to offer today is my perspective on essentially building a knowledge base, one that has sort of long endurance. And my perspective on this is really to sort of think about it as building a library. And I think there's still lots to be learned from sort of traditional library sciences in how knowledge is managed. And I would encourage people actually to shadow a librarian for a day to really sort of understand the depth and sort of the breadth of what it is that librarians have to deal with. So, you know, for instance, the acquisition of materials and determining what should be acquired, and then developing the metadata around those materials, and then dealing with the cataloging. And I cannot sort of describe for you how impressed I am with sort of the level of categorization that goes into library sciences. They work from giant manuals and guidelines to determine sort of how to uniformly put all of these acquisitions into their holdings. And then, of course, there's the standard record management problem that we're all familiar with, but then also preservation. And frankly, I think sort of one of the most important things about enduring knowledge bases is that we actually understand how to keep them vital and actually how to manage the preservation of them over time. So when I think of a knowledge graph, I really think about it in terms of something like the Library of Alexandria. And that is so that once we've actually learned something, we don't actually have to learn it again. We can build upon a foundation and use that foundation to actually enhance the new knowledge that we're bringing into the system. And I think, you know, trying to understand how we manage that as it grows so that we can actually find all of this information and use it in these ways is sort of still a very important trick that we are just barely getting a toehold on. And so I think that there's still much to be done in just sort of the management of large-scale knowledge graphs. I think one of the critical things that I think about in terms of these large knowledge graphs is that knowledge is actually being written down. And that is that, you know, once we actually know Angela Merkel's birthday, we would never encode it again. And I find it, you know, so interesting and actually sort of wonderful that Freebase, you know, is frequently cited in so many of the papers at this conference as being one of the data sets that people work on. My hope was always that, you know, the knowledge that is in something like Freebase or Knowledge Graph would long outlive me. And that's the reason that we want to sort of develop and organize these the way we are. So the idea is that, you know, you can put all of this information down one time and it's in some machine readable format and you can actually manage it at a very large scale. But even though it's in a machine readable format, I think one of the most interesting things about Knowledge Graph itself is that it's actually very human readable knowledge. And that is, you know, when I think about the quanta that is in Knowledge Graph, you can imagine sort of a wide spectrum of describing sort of what's actually in the graph. And for the most part, what we have in Knowledge Graph is very discrete. You can talk about sort of singular facts that answer questions. The fact that you can actually use this information without any context, the answers that are there don't depend on anything except sort of understanding the entity that you're obtaining that relation from. And in terms of verification, it really is universal. We don't sort of want this predicated on some subjective understanding of the world in which that fact was extracted. And so to interpret the data in Knowledge Graph, you really just bring yourself and sort of all of the things that you know as a human being, and that applies to literally anybody. And I think this is really important when we think about sort of the ability to verify the information that's in Knowledge Graph and the ability to actually go and correct the information in Knowledge Graph. Because one of the things that I'm really getting at is the idea that this data is semantically durable. And that is that I really see knowledge as something that ratchets forward over time. So the ability to actually observe what's in the knowledge base and then go and correct it so that new facts actually are integrated better, and to sort of manage those facts in such a way that we're actually increasing the value of all of the knowledge as it's accreting around those earlier facts is a very important sort of methodology and sort of one of the important attributes of knowledge graphs as I see them. So for knowledge graph, we have a few organizing principles, and one of the critical ones is a notion of identity, and that is obviously what makes things the same and what makes them different. We express these relations through what we think of as schema. But I think most important is also that we really see everything that's in knowledge graph as being discrete and identifiably unique. And then that uniqueness actually persists over time. We can differentiate every object from every other object, and that we understand sort of everything about an entity altogether on that entity. And therefore, this requires sort of the ability to actually merge entities together when we discover that we have the same ones, and to understand when they should not actually be merged, and how to actually cleave the world along these lines. So once we've actually gone through and identified sort of all of these different entities, then we can go and identify them persistent, durable identifiers. And we can use those then as the keys to access these entities over time. And literally things like the identifier for toaster has existed since about 2006. So these are very long-lived identifiers. When we actually put the knowledge graph together, one of the things that we think about a lot is actually how to classify the entities and actually determine sort of like what are the categories. And this seems like a trivial problem. And I think, you know, I find a lot of people in working with knowledge bases tend to take for granted sort of the fact that they know the class of the entities that they're working with. And when you actually start digging into how to define the boundaries of these categories and how to construct them in hierarchical fashions and how they relate, how the different categories relate to one another, you discover that, you know, it is far from easy. So a very simple example, which is a real world example, we had a group that was interested in building up the representation of fire stations in knowledge graph. And so, you know, I think everybody has a prototypic notion of what a fire station entails. There are fire people and there's equipment that can be used for putting out fires. But the question is sort of, you know, what does it take to actually form a fire station? What things will be identified as a fire station and what things won't? And as you start to go through the examples, it starts to get, you know, a little bit more tricky. So if you have a volunteer fire department and they actually don't have a place where all of the fire people congregate, and they actually just have equipment cached throughout the community, is that actually a fire station? And I think it really, you know, the definition of fire station not only depends on sort of like these intrinsic attributes around it, but also what you intend to actually do with it. And I think that's a very hard question to sort of get your arms around, because you then start to think about sort of what is it that I'm going to want to do with this in the future, and how is that going to actually be impacted by new data that I'm actually going to be collecting. And so as we went through and started to answer these questions, we thought, well, you know, we understand that most volunteer fire departments don't actually have places where the people are located all the time. So the idea that, you know, this is where we can actually go to obtain fire fighting services, that sounds great. And then you get to questions as to whether or not the dock that the fireboats are located on in different cities actually constitute fire departments or fire stations as well. And so, you know, depending upon sort of the city, if you're in Venice, if you're in San Francisco, fire stations with fireboats are not uncommon. So you start to think that maybe these qualify as fire stations if the volunteer fire department qualifies as one. But then you get into very interesting situations where you have aircraft that are located at civilian airports. And this is an example of one of the largest firefighting tankers in the world, located in Sacramento, California. And so the question is now, does the airport in Sacramento get classified as a fire station? Again, we have just sort of a cache of equipment that's used in a very specific type of firefighting scenario. And so, these questions sort of like keep building upon themselves. But it's really important that we actually understand how to draw these boundaries so that we can actually have a notion of fire station which is stable over time and to which we can actually accumulate new knowledge. So along with class identity, we worry a lot about entity identity and what makes an entity the same or different from another. And again, this seems so easy and intuitive, but the question is sort of like, on what dimensions are you actually going to start carving apart different entities? At what level of granularity is it interesting or important to actually start separating these things from one another? And so, it's easy to say, well, I understand the difference between a toaster and a kettle. Both have heating elements, and one works well with liquid and the other doesn't. And then you add things in like blenders and you start to say, well, okay, so there's something else about these that I have to take into account to describe them. And yet, all of these things as kitchen appliances, you start thinking, well, okay, now we need to differentiate these things from other types of tools that are around the house. And sort of all sorts of other equipment, and you do this for 5 billion entities. And you start to decide that actually the decisions that you make today are very, very important, because if you don't make good decisions today, essentially the problem snowballs in the future. One of my favorite entity identity questions is around sports teams. And so, this is a question of sort of what constitutes the same sports team over time. So the Victoria Aristocrats actually had many different names over the years, and they actually played in many different leagues, many of which don't exist anymore. And so the question is sort of, when does the Cougars that were in the NHL differ from the Cougars that were in the WHL? And again, we have to sort of come up with very sort of practical decisions about these things very early on, so that as we actually obtain more information that in fact there was a Cougars that was in the PCHA, we actually understand how to separate them. So you could say, well, it depends on sort of, the team name and what league they were playing in. And then you discover that, in fact, they've played all over the place. Literally many of the same players transitioning in these different locations in these different leagues. So again, trying to figure out sort of how we're going to model these things so that we actually have consistency over time, and we understand how to accumulate new facts onto information about sports teams. The granularity actually really matters a lot, and you can sort of think about different ways of sort of breaking down the world. So, Beethoven's Ninth Symphony, great, we have a representation for that. How about Leonard Bernstein actually conducting Beethoven's Ninth Symphony? Well, Leonard Bernstein actually conducted it with a number of different orchestras, including things like an orchestra that was composed of many different orchestras and actually had many different vocalists. So, it gets more and more complicated, and you need the ability to actually adjust these things. And then, of course, when you come to modeling it, you discover that it comes in 4 movements, and that those are actually very important to be able to describe so that you can find them and annotate them with additional information. I think, again, it's very easy to sort of think that, record merging and reconciliation and all of the different terms that have been applied over the past 50 years to this information sciences problem, we want to treat it like it's a solved problem, and yet very simple cases like understanding sort of the relationship between all of the different notions of the story of Total Recall, and actually understanding sort of the fact that, books about that actual production then develop names of the production get incredibly complicated. And I have to tell you that, again, sort of managing all of these different relations across media and all of the different names and things like that, understanding when it is that you actually have a cinematic release and determining sort of all of the different formats that release may come in and all of the different places where that release may have taken place are sort of a part of what it means to get your hands around entity identity. But of course, there's also relational identity. And so it's not enough for us to say we actually understand how to talk about a structure's height, because of course there's the structure's height, with antenna, with mast, what was the highest, occupiable level of the building. All of these things have to have some relationship to one another so that we can answer basic questions, but we can also understand and answer more complete questions, that dive into the deeper semantics. I think, another one is you think about sort of like who is the architectural structure designer. And, it's very easy to attribute it to some architect, but perhaps it was, actually something that should be attributed to the firm, attributed to a lead within the firm. And again, we want to be able to answer these things at all of these different levels of granularity, and we need that representation. And so this gets us into a world of really high precision semantics. And so this is, as I was describing, watchmaker, clockmaker semantics. And so we want to make the distinction between the religion and those practicing it. The island in which a country subtends, but if that island should be described as a geographical region separate from the country, we have to make those determinations. If you ever want to entertain yourself, go trace the history of the Remington Rand Corporation through the Remington and Sons, through the typewriter company, Remington Arms, Sperry Univac, Unisys. It's a crazy timeline where you actually need to have sort of different levels of granularity and resolution to understand sort of how all of these things fit together, and yet have the ability to talk about them in such a way that you can do the proper retrievals on it. So this really gets me to sort of like the core problem that I worry about all the time, which is, identity is very core to how it is that we manage the knowledge graph. But yet, how is it that we actually make sure that we're not just sort of arbitrary in how we actually segment the world? And then once we've decided how to do that segmentation, how do we make sure that we've applied it uniformly? And so when I think about sort of like where this leads, it leads us to a lot of what I think of as semantic hand-wringing. For all of the organizations that are out there, people want to be able to describe the Museum of Modern Art in New York. But Museum of Modern Art is, a collection. It's a physical location that actually has subsidiary locations. It's an organization that is responsible for the employment of people and for publishing books and controls the rights to a lot of media. And so we want to break those down so that we can actually answer questions and understand the world and the relationship between all of those things. And yet, when people ask us questions about the Museum of Modern Art, for the most part, we colloquially don't actually make these types of distinctions. So the more I think about this problem, the more I start to think about sort of what I think of as semantic neighborhoods. And so there was a point in time where if you asked about the New York Times circulation and you thought about sort of all of these different facets of the New York Times, you'd say, well, actually there's a publication called the New York Times that the New York Times produces, and so therefore that must be what you're talking about. But in truth, the New York Times actually owned the Boston Globe. And so when I talk about the New York Times circulation, I should be able to actually say, look, actually, I'm thinking about this at different levels of granularity and understanding sort of how to actually expand out this graph so that I can actually talk about sort of entities at different levels of granularity becomes very important. And so this is, I think, the biggest challenge that we face as we grow very large scale, long-term knowledge graphs. And that is the way that we talk about the world and the way in which we want to model the world don't necessarily coincide. And yet it's the way that humans and actually a lot of the information sources want to talk about this stuff. So I say that I live in San Francisco and that I grew up in St. Paul, Minnesota. And the truth is that neither of those things are actually correct. I live very close to San Francisco and I grew up just north of St. Paul. But you know, for anybody that I talk to who is not in that actual area, I'm going to talk about it in these very general terms. We want to know whether or not Tylenol can have side effects, but the truth of the matter is that a brand actually can't have side effects. The things that the brand actually produces and sells under that brand name can have the side effects. So these subtle things actually turn out to be sort of real trouble when it comes to semantic modeling. And so one of the things that we've been experimenting a lot with, and I have to credit my colleague Andy Vajda for really opening my eyes to this. We had developed a lot of very high level semantic relationships so that we could actually understand sort of the general notion of something contributing to another thing, or that something actually had an origin. And Andy took these ideas and said, actually, when you start using them in combinations, you get very interesting results. So that if you think about sort of all of the subproperties associated with a very high level notion of contributed to, and I say, I'm interested in, you know, what contributed to Star Wars, I then go through this list and produce some small result set. And when I actually intersect that against sort of all of the possibilities for origin 2, it turns out that I actually get a very, very tight result set, one answer, Harrison Ford. And in cases where I don't, other interesting things start to happen. And so I think this ability to actually think about both very fine-grained semantics, but also understanding how relationally loose semantics, when used in interesting ways, can actually produce the same kinds of fine-grained results is actually a very interesting idea that gets us out of a lot of this semantic hand-wringing. So one of the things that we've found very useful in organizing knowledge graph is to think about very high-level, categorically loose semantics as well. So we can, you know, qualify things as being agentive or non-agentive, as being animate or inanimate, categorical or individual. And when we actually use those things together to describe the different entities, you start to see sort of interesting patterns emerging. And so when you then combine these categorically loose semantics with the relational loose semantics, it turns out that you actually start to also get into a fine-grained semantic division. And so I think, you know, one of the interesting things about sort of bringing all of these things together is that, you know, the semantic durability and the ability to actually have these types of notions of semantic identity coming together allows us to talk about the kinds of strong identity that we want to have without necessarily going overboard with precision semantic instruments like we've done in sort of our clockmaker semantics. So I believe that durable identity is really sort of the way that you ratchet knowledge forward. You do it with some human intervention. And I think when you use it in combination with other types of semantics, we actually get a lot more power out of the system. Thank you.
Thank you, Jamie. I guess we'll start with the questions that we have. The first question comes from Dan Bickel, who says, it seems like the issues relating to granularity are intimately related to an ability to encode things compositionally, right?
Yes, I would definitely agree with that characterization. I think that, you know, one of the problems when you start actually opening the doors to sort of compositionality is that, again, you want to have some sort of semantic description of how that composition is taking place. And it turns out that, you know, as we pursue those types of questions, questions of compositionality themselves turn out to be equally as challenging. And actually, I feel that that's an area where we have lots less to fall back on. that not enough work has really sort of looked into sort of all of the different ways in which composition takes place. When you talk with linguists, many of whom I work with, I am amazed, I should say, at the level at which compositionality in language has been, studied and taken apart. Though I must say that, again, it doesn't feel like we have sort of like strong bedrock to stand on there. But I do think that as these two worlds come together, more interesting things will come out of that.
Great, thanks. Next question comes from Anne Kokos. It's hard to get granularity right the first time. Do you have any rules of thumb you use to make it simpler to adapt the schema as time goes on?
That's a really good question. Keeping schemas simple is useful. I think, one of the interesting things is to make sure that you don't paint yourself into a corner. And we have certainly made plenty of those types of mistakes and I must say that once you've actually accumulated a lot of knowledge and it's actually in use, then trying to sort of like figure out ways to sort of back out of those problems are a real challenge. I think, those top level categorizations and using them to sort of like guide us in terms of the creation of categorical structures below to prevent the types of conflations that we don't want has been sort of actually very instructive. Interestingly, I don't feel that we have sort of that same level of guidance for relational semantics. And this actually gets to the compositionality question. I do feel that that's an area where we at least don't have sort of as much experience and haven't found as much to rely upon.
Interesting, thanks. Next question is from Andrew Sue, who says, does your vision where any bit of knowledge was only structured once imply a need for a community knowledge graph? How do we, as individuals and companies, incentivize that?
I'm wholeheartedly a proponent of this, which was, in part my passion for Freebase and why I've been so excited with some of the Google releases. I really believe that, in the current state of the world, Wikidata is really sort of, the best opportunity forward for the community. But I do believe that, more sort of community participation in sort of, developing sort of good structural models and things like that, and good notions of identity is really important. So yes, I'm a huge proponent of that.
Great. Next question is from an anonymous person who says, could you discuss the relationship between knowledge graphs and their provenance or evidence?
Very good question. And I think they are deeply intertwined. And I believe that, a lot of these questions about sort of granularity and things like that are answered in part through a good management of provenance information. So that as you start to accrete things together, you actually understand potentially how they should be broken back apart for reaggregation. Now, the problem, of course, when you do that, is that the semantic durability, our ability to talk about sort of references and things like that, changes dramatically. And I think, that type of semantic management is, again, an area where being able to actually follow the provenance of an object through its semantic life cycle is really important. But it really does, I think, in part go back to sort of the origin of the data. And it is, I think, an area which probably has not received as much attention as it should.
Great. Next question is from Zach Ives, who says, regarding the notion of equivalence, as with your example of San Francisco, this often seems to depend on the question being asked. Is there a way to capture this?
I don't know. And I should say that we have, I'd say, various cribs that we use actually in knowledge graph to understand sort of different levels of granularity, the boundaries that you might be drawing around different objects, so that we can actually answer these questions in meaningful ways. I actually think, though, that part of the trick, and this is an area where, again, I credit Andy Vajda for having done sort of the most interesting sort of work, is the ability to look at an entity and discover that sort of for the context of this question, or for the, I should rather say, the answer that you're generating, given the context of the question, it doesn't seem right. And therefore, you actually want to sort of expand the notion of that entity. You actually want to get into its semantic neighborhood. And I think the mechanisms through which you actually do that are very, the few that I've sort of seen in practice now, are very interesting. And again, sort of like an area where understanding how these semantic neighborhoods are actually used, I think is a very sort of rich area for pursuit.
Great. I think that's all the time for questions that we have, and we can move on. I guess. Thank you.
Thank you.
And move on to our next speaker.
All right, thank you. I'm very happy to introduce our next invited speaker, Xin Luna Dong. She has been a principal scientist at Amazon since 2016, leading the efforts to build the Amazon product knowledge graph, and also managing the team of scientists conducting research on knowledge management, data cleaning and integration, information extraction, graph mining and embedding, knowledge-based search and recommendation. Prior to Amazon, she was a researcher at both Google and AT&T Labs Research, and she recently gave tutorials at Wisdom and ACL and KDD. Her PhD was from University of Washington with work in databases, and she has a VLDB award in early career research contributions to, quote, advancing the state of the art in knowledge fusion. So Luna really is the ideal person to help bring the database community to AKBC, and we're so pleased to have you with us, Luna. Please join me in welcoming her.
Thank you very much. So is screen sharing good?
Yes, it is. Looks good.
Okay, sounds great. Thank you. Hi there, this is Luna from Amazon. It is my great honor to speak here about our project Ceres, where our goal is to harvest knowledge from semi-structured web. And here I put a picture of the goddess Ceres, and she is in charge of harvesting. And the internal name of the project at Amazon is a Greek goddess with the same responsibility, but different nationality. Okay, so before we talk about Ceres, let me tell you a little bit about what we are doing at Amazon. We are trying to build a product knowledge graph with a mission to answer any question about products and related knowledge in the world. With such authoritative knowledge for products, we hope to improve Amazon search, recommendation, voice shopping, and so on. To help you understand what is a product knowledge graph and how that compare with a generic knowledge graph, such as a knowledge graph at Google, let's see a piece of knowledge graph example for two songs. So it is a graph, so it has nodes and edges. Each node represents an entity belonging to one or multiple different types. And for example, here we have two nodes for sound recording. And then each edge represents the relationships between two entities. So for example, for this song, it has the same artist and songwriter. That's a person whose name is Taylor Swift. To understand what a product knowledge graph is, let's squeeze it to one side and add the product parts. So these are all of the products, the tracks at Amazon. And we can see that multiple tracks might correspond to the same sound recording, and they might have different formats, they might belong to different albums, and so on. So to build such a product knowledge graph for media products, we actually have abundant data. And the publishers for media products such as books, movies, and music, they are very well trained to provide decent quality structured data. And so the challenge is that the different publishers, they use different format and they refer to the same entity in different names. For example, Taylor Swift and Taylor Allison Swift. As what we just heard from Jamie Taylor, we want the identity for each object, each relation, etc. So the key thing here is to resolve the heterogeneity. Given a whole bunch of data sources, we want to integrate the data. And one key component here is entity linkage. That is to decide that Taylor Swift from this source and Taylor Allison Swift from another data source actually refer to the same real world person. And then if we want to be cool, we also do knowledge fusion, where we try to resolve the conflicts from different sources. If we see two different date of births for Taylor Swift, we need to decide which one is correct or whether she was born twice. And if we want to be sexy, we get the data from the web. And this is because there are so many different songs, movies in the world, and the web really gives you a comprehensive set of information. So at our team, we are able to solve the entity linkage problem with a precision of 99% and recall above 90%. And for web extraction, we can do above 90% precision. So we are supporting more than 20 Amazon Music applications. And also our web extraction is supporting Alexa knowledge graphs for Alexa question answering. So now let's see another example for product graph. This is for retail products. So there are two products which are Tide detergent products, those two brown bubbles, and those green bubbles represent their variations with different scent, different sizes. And then we see they share a lot of property. For example, they have the same brand, same function, they have the same form, both are liquid, and neither of them is a high efficiency. And the product on the left-hand side, it has one extra function, auto remover. So talking about retail products, here we don't have that much of data anymore. And this is because retailers are not trained to provide structured information. Instead, they put the majority of the information for products into the texts, such as the titles and the descriptions of the products. So structured data is sparse and noisy. Just let's see this example from Amazon. This is some chocolate product, and we see very sparse information except the title. And even if we see some structured data like the flavors and sizes, but you really don't feel this 1 pound red rose box is a flavor and dark blue foils is size. So to resolve this challenge, what we need to do is we take the data from catalog and then we need to enrich it using data imputation. After that, we need to do data cleaning to clean up all of the messes. So at our team, we have developed this system called AutoKnow, which is self-driving knowledge collection system for products from many, many different product types. And we are able to increase the coverage of structured data by 12 times and increase the accuracy of the data from Amazon catalog by 8%. Currently, this is live on Alexa Shopping, Amazon Search, Detail Page, and so on. So for this talk, I will focus on web extraction. So although this is just one component of this big system, but as I said, this is the sexy component, and this is important for us to collect long tail knowledge to support Alexa question answering. Okay, so Ceres extract knowledge from semi-structured websites. And why do we focus on semi-structured websites? Let's first see a few examples. So here is a web page from IMDb, and we see that it is not a big article or a huge chunk of texts. Instead, we see a lot of attribute value pairs that gives us information about this movie. Here is another web page from a different website about a famous Indian movie. And here is one about a famous Chinese movie, and it is in Chinese. And most of the semi-structured websites, they are populated by some underlying giant databases and according to some particular templates. So different pages on the website look very similar. So we have observed a big promise from semi-structured data. This is according to the previous project I participated in at Google called Knowledge Vault. The goal of Knowledge Vault is to extract knowledge from all over the web. And in particular, we consider four types of knowledge sources. The first one is texts, the articles on the web, such as news articles. The second one is DOM trees, and this is the semi-structured websites we have just seen. The third one is web tables, the tabular information on the web pages. And the last one is web annotations according to schema.org in the HTML code. And the parenthesis gives the number of knowledge triples we extracted automatically from each type of data sources. And we can see that 80% of the knowledge are extracted from semi-structured websites. And if we look at the extraction accuracy from Knowledge Vault, it is 52% for web texts and 63% for the semi-structured data. It is better, even though it is not ideal yet. So let's see what are the opportunities from semi-structured data. And here I want to use the largest iceberg in the world as a metaphor. And this is partially because semi-structured data is like a huge iceberg with a lot of information. And here is a page from Rotten Tomatoes about the movie When Harry Met Sally. And we can see the information on some of the attributes for the movie that we are familiar with, such as the genre, the director, the writer. And these are the information normally modeled by ontologies such as the free-base ontologies, as we have just heard from Jamie Taylor. And this corresponds to the part of the iceberg that is above the water. And in addition, there are attributes that we are not familiar with, such as in theaters, on district streaming time. And we did some analysis on 10 popular semi-structured movie websites. And we looked at IMDb ontology and found that the attributes mentioned in IMDb, which is quite comprehensive, covers only 7% of all of the relations modeled by these 10 semi-structured websites. And so the information here is like the part of the iceberg below the water. In addition, there are a lot of domains, such as the Broadway shows, the video games. These are the unknown domains, and they are like the part of the iceberg that is deep in the water. So where were we in the extraction now? Well, we're at the tip. So we heavily rely on manual annotations to reach high precision. And as I said, for automatic extraction, the precision could be quite low, 60%. That is definitely not enough for industry production. And also, we're restricted to existing schema from existing domains. And we have good quality typically only on easy attributes, like the attributes with single value, like the date of birth. So why is this so hard? It seems to be quite regular web pages. Why is it hard to get good results? There are at least 3 challenges for knowledge extraction from semi-structured web. The first one is, even though in the same website, the web pages look quite similar, populated by the same template, the formatting can still vary slightly. Look at these 2 pages from IMDb, and we can see that because of some missing attribute, etc., the layout is not exactly the same. And the second, the data could be formatted totally different from different websites. And it is hard to imagine to train one single model to extract from all of these different data sources. And finally, with the big variety from different websites, because there are so many different semi-structured websites, it's impossible to manually collect the training data for each predicate on each website. So where is the hope? Can we get the whole iceberg? So to answer this question, let's first see what are the clues to do extraction from semi-structured websites. The first one, with no surprise, is the DOM tree. So this is an IMDb web page, and this is the HTML code behind it. And we can see that these are nodes in the tree structure, and each node has an HTML tag. And meanwhile, it has the ID, the class, and also the text information. So this gives the traditional methods. The first one is wrapper induction. We collect annotations for each single attribute. And then we try to reverse engineer what is the XPath to extract such information, like here. And wrapper induction could get very high precision, above 95%. However, this requires a lot of manual annotation. And an automatic solution tries to train extraction models using distant supervision. And here we look at some seed knowledge, for example, from IMDb, and we look at the subject and the object on each page, and then try to apply distant supervision to automatically generate the training data. The training data is very noisy, and so the extraction precision is only 63%. So the next clue is the site-wide template. As we said, all pages are generated from the same template in a website. So we try to leverage the consistency among the different web pages. This gives AutoCeres, which can do automatic extraction from the websites with much higher precision. And there are two technical points behind this project. So first, it leverages the site-wide global information. So it does not train a model just by looking at each single page. It does not generate the training data by just looking at each single page. And it tried to make the page level local decision according to the global consistency. And the second, it does two-stage extraction. It first identifies the topic entity or the subject from each page, and then identify the attribute value pairs for that subject. With these two key intuitions, we are able to increase the precision from 63% to 90%. 90% basically means now there is hope to productionize it. So this is some results from an experiment where we look at 33 long tail movie websites, including 400K different web pages crawled by Common Crawl. It has English and 6 other languages, and it has a lot of long tail domains such as animated films, documentary films, and so on. So we are able to automatically annotate 16% of all of the pages. For every annotated page or every annotated entity, we're able to extract 2.6 entities, meaning 1.6 new entities. And for every annotated triple, we're able to extract 3 triples, meaning 2 new triples. And this gives us an extraction of 1.25 millions of triples with a precision 90%. And as this plot shows, as we vary the confidence threshold, we're able to control the precision. At this point, we get the precision of 90% with 1.25 millions of triples. Okay. The next clue, if we look at the page, actually there is a lot of information hidden in the layout. So let's look at these 3 attributes we already know, and we see how they are vertically aligned and horizontally aligned. And this helps us to guess in theaters is another predicate, and the value is July 12th. So using this kind of clue, we worked on this project called Open Series, which allows open information extraction to extract knowledge for attributes that we don't know yet, not in any existing ontology. So the key technical idea is weak learning. We generate the weak labels according to the labels that are generated using the seed knowledge. The precision is lower, it is 65%. However, we can increase the number of attributes by 10 times. Here are the examples of how we can enlarge the set of attributes. Taking university as an example, our seed knowledge contains only 3 attributes: phone number, web address, and type. And we are able to identify a lot of new attributes like the calendar system, enrollment, highest degree local area, so on and so forth. So this is extraction on the same set of long tail movie websites. This purple line is for closed IE for auto series, and this green line is for open IE for open series. We see that we added significant amount of knowledge. And on the other hand, if we look at the knowledge for newly discovered attributes, so the precision is still low, and we still need to work on increasing the precision. With that, we can go from the iceberg above the water to somewhere below the water. Okay, the final set of clue is the visual patterns. And before I tell you what is the visual pattern, I want to do a quiz with you. So I don't know how many people in the audience understand Korean. So I'm hoping actually most people don't understand what this page is about. However, even though you may not understand the page, you may not understand every single Korean word on this page, you might be able to guess what is the topic entity on this page. So that is this part. This part represents the topic entity, the subject, and which part represent an attribute for this topic entity. All of this should be, and here is an example. And what are the values for this attribute? This is one value, and there can be a few other values. What are other possible values? This is possibly another value, even though we don't know which is the predicate. So see, even if it is a page you have never seen before and you even do not understand, as human beings, we can reason about it. So what is the underlying pattern behind it? And that's the visual pattern. So this includes the font, the color, the size, and also the location of the text on the whole page and the alignment of the text fields. So leveraging this intuition, we got zero-shot series, which allows us to extract knowledge for new domains where we even do not have any seed knowledge. So the key technical part is a graph neural network. And we use that to learn representations for each text field. So our F measure is 46%, both precision and recall is around 45%. This is not high, but comparing with baselines, like looking at the semicolon, we significantly increase the recall. So here is the extraction on all of the domains where we might have the training data, and also on the domains where we do not have the training data. We can see that for those new domains, our result is only slightly worse. And this gives us the whole iceberg. Okay. So next, let me talk a little bit about how we do such zero-shot extraction. And this is our latest results and how we leverage all of the evidence I have just mentioned. And here I want to call out the key contributors for this project. So the key technique, as I said, is to leverage the graph neural network. And to apply graph neural network, we need a graph. And the graph is generated according to the page layout. Each node is a text field, and the edge represents their layout relationships or DOM relationships. The purple lines, purple edges represent the left and the right relationship. And the yellow edges represent the up and the down relationships. And the green lines represent the DOM relationships. Basically, these are nodes that are siblings or cousins in the DOM tree. Look that cast and the crew, even though they are a little bit far away on the page, but on the DOM tree, they are siblings. And for each text field, we look at 2 different kinds of features: the textual feature from BERT embedding, from the IDF across the website. Cast will appear very often on different websites, whereas particular person names will not appear that often, and also the text length. And for the visual feature, we look at the font size, whether it is bold, underlined, italic, what is the font color, what is the text field dimensions. So let's use this as an example to see how we train the model. For this mid-college with acceptance rate and tuition, we get the visual and the text features for each field. And meanwhile, we get the page layout graph. We feed that into a graph attention network, and this allows us to propagate the information among the neighbors. And then we can get the contextual representation of each text field. To do closed IE extraction, where we extract using existing attribute set or ontology, we take the visual feature, the textual feature, and the contextual features and feed it into a multi-class classifier to decide for this particular text field what relation it is talking about. And for OpenIE, we take a pair of text fields like tuition and $53,000, and we generate some pairwise features by combining their individual features and feed all of them into a binary classifier to decide whether that's attribute value pairs. And for training, we have a pre-train step on simplified IE tasks. So basically, we try to decide for each text field whether it is a relation string, an object string, or some other strings. And after we do the pre-training, we will freeze the GNN weights and then train the extraction layer for closed IE or open IE tasks. Okay. So now this is regarding what results we have got and our latest techniques. Are we there yet? So there are several future works. First, we still get quite low quality precision for OpenIE and for new domains. Can we improve the extraction precision to above 90%? Because in industry, that's the minimum for consideration of production. And here we can possibly, for example, combine the zero-shot learning with distance supervision. And second, inspired by BERT embedding, etc., can we learn some representations for the semi-structured data to support not only information extraction, but other applications such as question answering, search, and so on? And finally, can we align the knowledge from millions of the sources after we do the extraction? Can we link the entities across different sources and types? And can we align the relations in OpenIE? Here I have some shameless advertisement for a paper presentation we have for tomorrow. This is regarding entity linkage. Okay, several takeaways. We aim at harvesting knowledge from all of the semi-structured data on the web, and we aim at high accuracy. And meanwhile, we are open to extract new entities and new relationships. I want to let you know 2 benchmark data sets. We extended the SWDE benchmark for knowledge extraction from semi-structured websites. And in addition, we have this data integration to knowledge graph challenge dataset, which not only provides you the extraction dataset, but also for entity linkage and for schema mapping. Okay, thank you very much. any more questions, I guess there should already be questions on the chat channel.
Wonderful. Yes, thank you, Luna, so much. There are many questions here. So the question at the top is, the Google Knowledge Vault project was halted. Information extraction into KG at Amazon seems to be working better. Is this true? And what technical differences are there in the problem setting or methods?
Okay, that's a great question. And for Google Knowledge Graph, it gives birth to a whole set of, Google Knowledge Vault, it gives birth to a whole set of technologies. And some of the underlying techniques are launched in some of the Google applications, production applications, for example, for Google Assistant. And there are two lessons I personally learned from that project. The first one is we need to get really high precision. And this is why I have been emphasizing 90% precision all the time. And the second lesson I learned is Knowledge Vault does not extract knowledge for new entities and for new relations. So all of the knowledge is among existing entities in Knowledge Graph in Freebase. And consider those like popular entities. We already know all of the popular facts. And what we could extract automatically from the web are oftentimes the long tail knowledge for popular entities. It is not really required or like in demand that much. And for this new project, the Ceres project, we focus on identifying new entities and even new relationships, because those long tail entities, when we get popular facts for those long tail entities, actually collectively, it can be a lot of impact.
Thank you. Next question. Products are particularly strong examples of entities at multiple levels of granularity that Jamie Taylor described in his talk, mentioning Beethoven's knife and its different versions. Your thoughts about this for products, I suppose.
Sure. That's a good question. So for products, we seldom say, okay, these 5 different products, we consider them as different. As far as a like a customer, you get one of them, you get the second of them, you cannot distinguish it. So we do not make that kind of distinction. And then it is much more of, if we say it is the same product, if you get it and you cannot distinguish it and you feel happy. On the other hand, this different granularity actually appears a lot for product types. And believe it or not, we have 100,000 different product types at Amazon catalog, and we are still able to identify more. And that gives huge challenge in terms of automatically construct and enrich the taxonomy, and also categorize each product to oftentimes multiple different categories. And the third, when we train any imputation and a cleaning model, how to make it work for hundreds of thousands of different product types, because each one has its unique feature.
Right. I just follow up on that. I imagine that in some cases, 2 products that would be highly related, like a recording of the same symphony, but on CD versus some other format, yes. Maybe should appear on the same product page, and then for some other products, they should be made separate based on similar attributes. This happens, sure. And how are these decisions made?
Yes, yeah. So this is what we call variations. For example, we could have a whole bunch of different Tide detergents that have different scents and sizes, but that's the only difference. And certainly different customers will have different preference, but normally the price will be quite similar. And also the comments for this customer reviews for these products in the same family would be quite similar. And this is actually a perfect advertisement for our paper that will be presented tomorrow.
Excellent, wonderful. All right, next question. You mentioned BERT embeddings as input to your GNN training. BERT is often great for context-sensitive embeddings. Does that matter here for such short fields?
That's a good question. And so we use the pre-trained BERT embedding. So we can tell, for example, a director and a directed by this have some similarities and they are likely to be predicates. And on the other hand, the names, their person names, etc., they are likely to be the objects. And we see more improvement for closed IE, but less for open IE.
I see, right. So even if the text you're representing is just very short, they're just one or two words of context still find it helpful.
That's true.
All right, yeah. All right, the last question here on the list here, just with the right amount of time. William Cohen's invited talk discussed answering queries requiring multi-hop logical reasoning. Do you think Amazon users would use this? And what would its technical requirements be?
So what I found is whatever William Cohen said, this will be either useful now or very useful in 5 years. So I wouldn't question that. And in addition, I really like the morning session from William, from Yuri regarding considering multi-hop QA as knowledge inference. And I can see a lot of interesting applications out of it.
Wonderful. Luna, thank you so much. I will clap for the large
you.
audience that we have here all together and turn
Thanks a
things
lot.
back over to Samir or the program chair, I don't know which, to describe next steps. Thank you again, Luna.
Thank you, Luna.
Thanks.
Now we're just going to have our hallway chats. And I think there are virtual booths there for people to attend. There are invited speakers who will be available to chat. I think Yura is going to be late by 30 minutes. And there's also a random chat session as well. So I encourage everyone to go there, hang out, talk to invited speakers more. And we'll see you in the live session tomorrow morning. Thank you.